Sharing. Sharing. Yeah, we should do these. We might have to restart this. Oh, it's like good. Yeah, once YouTube machine there. Did you read the content or did it get put on the website? Maybe share.
So people where there is a student in the particular translate.
That's
free. My presentation, not and where is your presentation?
That's one, two.
Sure. I don't
Two. That's one, two. That's one, two. That's one, two.
Okay.
That's one, two.
Yeah.
We're not sharing it yet, honestly. I just say it's
Yeah.
Sharing. That's one, two. That's one, two. That's one, two. That's one, two. Spell wrong.
Yeah. Or you should free.
That's one, two. Still no. Question says one, two. That.
First.
I don't know if that's a setting that's, I think we might have the wrong thing, but
It seems like we've seen. Kaylin, can you check if there's people in the waiting room?
Yes, there are. There are people in the waiting room, but they might not be able to hear us, because I can't hear you. Here, I'm gonna admit them to be extremely. So maybe I'll get started.
some of them will not.
I'll admit them, but I might have to restart this.
The end of expresses that are assuming that it's the free course and so they. I know, so we in the right line.
Hello, testing one, two, testing one, two. Ask me a question on Zoom and they.
Can you hear us on Zoom?
Have a nice weekend.
You too. Bye bye.
Sounds good. Yeah.
Yeah.
Yeah, they said yes. You said yes. Should we?
Okay. Okay, I guess we can get started. Can they talk on Zoom? Have one of them talk.
Can one of you talk? Yes. Seems to be fine. Okay, so we set.
Almost, I gotta disable the waiting room.
In the presentation.
One more. Okay. Waiting room disabled, admitting all. Are there any remote presenters?
Yes.
Yes, can you ask Mary Ann to talk or Stefan, somebody talk on Zoom, please.
Can someone, Shereen, can you speak? On Zoom?
Yeah, hello, can you hear me?
Yeah.
Very low.
Yeah, it's pretty low. Yes.
Very well.
Hello, can you hear me? This is Mariam Sultana.
Okay, so it depends on actually who's speaking.
Yes, I'm gonna turn it up here. Yeah, that's the speaker. Yes. Hold on, let me make sure, That's one.
Okay, thanks. But if you're all set, we can start today. It's going to be pretty long programs. We'll get started. Welcome to this workshop on epistemic uncertainty in AI at UAI 23. I hope you can see the screen all right. My name is Fabio Puzzolin, and with Kevin Shayat Madar.
Just read this.
It is from there, but here still looks
Still
like
there.
screen sharing. You see the introductory panel on Zoom?
Or you can see the.
That one, yes. That's the main. So they seem to be able to see it on live, but not on the screen. Sorry, just give me so we also people connected or chats.
Hold on, that might be me. Hold on.
All right.
Okay, we go.
Okay.
We're back.
Yeah, back. Okay. Sorry for the slight interruption. So welcome to this workshop on epistemic uncertainty in AI. I'm Fabio Puzzolin. I'm the principal investigator for the Epistemic AI European project that kind of funds this event. And I'm here with Kevin, who's the main co-organizer, but there are other organizers I'd like to mention: Mariam Sultana, my research fellow, Shireen, Shireen, and several others. This is supposed to be the initial schedule, opening remarks, which I'm trying to produce now, and then a brief introduction to the Epistemic AI project. We have 4 invited speakers today. Herta Kuman, then we have, I'm trying to get to the right order. Marco Zaffalone is the second speaker, and then there's Yarin Gao, and finally, last but not least, Hadith as so you itself. I'd like to give a little bit of an introduction to the Epistemic AI project, which is provides the rationale for this workshop. Manage. Can you just share to the other presentation? There you go. Thanks. So I'm quite pleased that we got a good number of papers submitted to the workshop, around 15, 20 papers, and most of them were high quality and were accepted in the form of poster or spotlights or oral presentations. So there's good interest in this team in the community, I would say. I would argue that probably there should be more interested than this even, because this is arguably the biggest problem machine learning has. And right now there isn't enough attention on this. And this is one of the reasons why I use this Horizon 2020 project. If you're from Europe, you're familiar with the funding system there. There's a overarching framework called Horizon, and now it's called Horizon Europe. Before it was called Horizon 2020. This was funded as a future emerging technologies project, so it's sort of a blue sky stream of projects with an acceptance rate of around 5%. So very, very competitive. So it's a project with a budget of 3 million euros and just 3 partners. There's ourselves, Oxford Brookes University, and me. And there's also KU Leuven, represented here by Keva and TU Delft in the Netherlands. These are websites, so you're more than welcome to check the website for more information. So what is the bottom line of Epistemic AI, which kind of gives a name to this workshop? The idea is that the current form of artificial intelligence is really unable to deal with epistemic rather than aleatory uncertainty. Although the Bayesians will disagree, obviously, but there's certainly more work to be done to properly model epistemic uncertainty. So uncertainty on the models themselves, uncertainty on probability distribution themselves, based on the data that is available to you. And the objective of the project is to reimagine AI for proper treatment of the epistemic uncertainty that stems from partial knowledge of the world. Technically, this is done by injecting into AI machine learning, especially techniques from mathematical uncertainty theory. So this is a consortium. There are 3 academic partners. There are no industrial partners. There's us, Oxford Brookes, and there's KU Leuven, and then there's TU Delft. So Belgium, Netherlands, and UK. These are the senior investigators, myself, and then there's Rita and Bradley, who's an expert in autonomous driving. In KU Leuven, there's 2 associate professors, Alex and David Mens, and Kevin, who's the main motor of the work on the Leuven side. TU Delft, there's Neil York Smith, Matti Spahn, you might know, who was one of the program chairs, one of the big conferences recently, an expert in reinforcement learning. And Julian Koki, who was also an expert in driving. Why I mention autonomous driving? Because the validation of all these algorithms and frameworks is within this project is done in autonomous driving. So this is a concept. This diagram is a bit out of date because I have newer versions of this. But the general idea is that we want to reverse the usual machine learning style that you learn a model from a limited amount of data. You use this model to explain the training data and put it to the side, which is illustrated by the orange stuff here on the left and right on the training set. To another one, to a completely opposite point of view, in which you start from a state of complete ignorance. So every model is compatible with no data, basically. And then you use the training data in dark blue just to restrict the set of models that is compatible with the observed data. So that was my original intuition. My original intuition is we need to reverse the process and use the available data to narrow down the constraints on the true model, on what the true model is, basically, that explains the data. And that evolved over time, because I was thinking, how do I actually do this? Because there have been attempts to do like learning sets of models, and obviously there's ensembles and there's various techniques. What we're trying to do in this project, we want to use, to this extent, uncertainty theory, which is an array of formalism devised to encode second-order epistemic uncertainty. How many of you are familiar with non-probabilistic uncertainty? Can you raise your hands? You are for sure. So why are you nervous? Okay. Anybody else? There's a few, very few, as usual. So probability theory is, to your surprise, or most people's surprise, not the only mathematical framework for modeling uncertainty. There's many others. And most of those focus on epistemic uncertainty. They use more complex measures that often amount to convex sets of probability distributions, for instance, lower and upper probabilities, so-called probability boxes, random sets, or cradle sets. So there are various different versions. There are also behavioral and betting formulations as an imprecise probability by Wally. What we want to do in epistemic AI, we want to use this higher order uncertainty theory to model the epistemic uncertainty associated with limited training sets. But not only, I mean, all sources of uncertainty, but I think the main one is definitely the fact that your training set is very, very small compared to the possibly very large or even infinite amount of data relevant to the task that you want to solve. In this slide, I'm making a couple of examples of what these uncertainty measures look like. So here in the top, you have P boxes, which are lower and upper bounds of the cumulative distribution functions. So you're familiar with CDFs from probabilities. So these are curves. Total probability of this interval up to here, these are curves that they go up monotonically like this. If you have a lower bound, or say if you infer from your data lower bound and upper bound, you have something called the P probability box or P box. This is something called a monotone capacity. You know that probability measures are monotone, so the probability of an event A, which is a subset of B, is not greater than the probability of B. But on top of that, probability measures are also additive. So the probability of the disjoint union is the sum of the probabilities of the elements. In monotone capacity, you only have monotone, you only retain monotonicity, you get rid of additivity, and you get more general uncertainty measured this way. One special kind of monotone capacity, apart from probability measures, is random sets, which I try to represent here. So imagine you have a die, you cloak, like two other faces of die. I cloak, you can still roll the die and get a face. Only sometimes you will get a cloaked one, and that is a set valued observation, because you only know that the cloak face corresponds. Forget about the geometric arrangement of the faces. You only know that the cloak face can be phase 1 or phase 2, but you don't know which one. So basically, you still have a random variable, but the outcome of the random variable is not going to be a set. So random sets are set value random variables, basically. In the finite case, they're called belief functions. If you've heard of the Dempster-Schaeffer theory, because of philosophical reasons, they've been given a name belief functions, but really these are set value random variables. So this is the plan for EPI or epistemic AI. So as you can see, it's pretty complex. So there's an uncertain world out there with missing data. Human behavior is very unpredictable, scarce data, limited or biased training sets. And this can be modeled by theories of epistemic uncertainty, which can also be injected into optimization to produce. This is actually Kavan's group's task, to inject techniques from epistemic uncertainty into constraint optimization. You all know that machine learning is basically a giant constraint optimization problem. Obviously, different models correspond to different types of constraint optimization. But how do you go about solving a constraint optimization problem under epistemic uncertainty? So if your objective function, your constraints are not just of a probabilistic nature, but of a more general, higher order uncertainty nature. So if you have a lower number probability constraint on your objective function, for instance, how do you solve such a problem? So once you have these two things in green, then you can create new versions of unsupervised, supervised, and reinforcement learning based on this epistemic learning principle. And we also pay a lot of some attention here to statistical learning theory in this project, and things like generalization bounds and epistemic uncertainty. Finally, validation, like I said, is performed under 3 different use cases that come from autonomous driving. I'm going to tell you a bit about those. So these are the objectives. creating your novel mathematical framework for optimization of epistemic uncertainty, formulating unsupervised, supervised reinforcement learning, validating these three new epistemic AI paradigms for autonomous driving, and more in general, fostering an ecosystem of academic research and industry partners throughout Europe and elsewhere. This is why we're here today with this, doing this workshop. A few examples of the work that we've done so far. This is a paper under review at NURIPS on random set convolutional networks, where instead of having a score for every class, you have a score for every possible sets of classes in the final layer. Obviously, we don't do it for all possible classes because this has exponential complexity on the size of the class list. But we do some relevance assessment based on the training set, and we select a number of relevant sets of classes, and then we produce scores just for those. How do you train such a network? You need to generalize classical cross entropy, and this can be done by, I think I have a slide for that. Yes. By the generalizing the Kullback-Leibler divergence. So you know that cross entropy is the KL divergence between the ground truth and the prediction. So if your prediction is a random set and your ground truth is, say, another random set, how do you measure the KL divergence between these two? So the loss function we're working on this kind. You can also formulate it as like having losses that represent lower number bounds on the likelihood of the training set, because again, cross entropy is can be interpreted as the likelihood of the training set under the model. We've done some work with my other PhD student, Mohammed, on identifying relevant sets for the problem ahead from the training set, which is what is described here. And then once you select these fixed budget of relevant sets, you produce scores in an output. You have an output layer for just those sets and not all the others. This is done using class training, basically. There are other ways, but this will be done so far. More in general, this is an example of what we call epistemic deep learning. So it's about formulating losses, not just for classification. That's why I mentioned the KL divergence. This is a brief representation of what a random set is. So you have a source probability up here, and then you have a one-to-many mapping to the problem, to the space for the sample space for the problem you need to solve. So if you have two random sets down here, you want to compute the KL divergence, you can go back to the source probabilities for these two random sets and compute KL up here, basically. This is the idea. There's also a difference between the target level representation and parameter level representation. You know that in Bayesian deep learning, the target is to learn a probability distribution of the set of weights or the parameters of the model. So that's what we call parameter level representation. And so you can, similarly, you can aim to learn, say, a random set on the parameter space for the model, which shows. You can also do target level representation, which is what the random set CNN diagram showed before. So you have, the purpose is to have a model that outputs an uncertainty measure on the target space for your problem. So the set of classes for classification, or the set of possible bounding boxes for object detection, whatever. So that can be extended to regression as well. So this is one of the things that we're doing. How do you infer a belief function or a random set from data? There are different approaches, and the two main ones are one due to Dempster, Arthur Dempster himself, and there's another one called weak belief by Ray Martin, who's a statistician here in the US, actually. We are doing work in supervised learning, in particular GANs, but also diffusion models. So, you know, diffusion models are cascades of basically Gaussians. Surprise, surprise. Welcome to the Bayesian world. And so how do you robustify that? So for instance, some ideas we have, you could sample from Creedal set, so it's convex set of probability distribution rather than a single Gaussian. So if you have a convex set of Gaussians and you have a two-level sampling problem, so you can sample first the Gaussian and then you sample from the Gaussian. So you have robustified version of diffusion model. This is what Mohammed is working on. You can also look at the loss side and replace expectations with lower and upper expectations in the losses. So that's another thing you can do. So Mohammed right now is looking at generating results from like this two-level sampling approach and see if they look more varied or more surprising than the results you get from standard diffusion models. You know, the images, they start looking, if you do image generation, images start looking pretty much all the same at some point. Can this approach be useful to add more surprise to the generation process? There's a reinforcement learning side. So here is an illustration of POMDPs, partially observable market decision processes, which are the mathematical foundation for reinforcement learning, as you all know. What happens if instead of having transition or emission probabilities, you have convex sets of transitions and emission probabilities represented by these polygons up here? Can you learn them from data, from exploration and the likes? It's a big problem, and this is what they are working on at the moment, and also partly here. Validation, like I said, is in the autonomous driving domain. So we created this new road event awareness data set for autonomous driving, which is basically a collection of 22 long videos of road events, which we call road events like triplets with road agents, the actions they perform, and the location they're in, compared with respect to the autonomous vehicle. And this can be used for test prediction, the modeling of complex road activities, situation awareness, future trajectories, but also even more sophisticated things like theory of mind stuff. So we released this ICCV 21, and now we have a new version, ICCV 23, which we call Road++, where we basically extended the same kind of notation to the road data set. So now we have both UK videos and North American videos, and we're also looking at extending this from videos to from the UAEs and India, so like multi-continent benchmark that can be used for serious domain adaptation. Not the toy data sets that people use nowadays, like rotated MNIST, that kind of stuff. So this is real data, so we are really spending a lot of time on that. Couple of extensions, I think the last couple of slides are possible future extensions of the epistemic learning idea, and one is continual learning. Because the epistemic AI principle can be naturally extended to continual learning. Actually, I argue that it makes more sense in a continual learning setting, which you keep learning from a series of batches of data, or individual data points, sets of data points. So you build your initial epistemic model and you keep refining them over time by combining these epistemic uncertainty measures either at the target level or at the parameter level, like I said. And so the epistemic uncertainty about the correct model for the data is continually revised in the light of new data correct. This stage grant application is currently pending with the UK Research Council. And another one I'm working on with a guy in UAI Amsterdam and also somebody at Amsterdam University is modeling epistemic uncertainty in neurosymbolic AI. Some of you work in neurosymbolic learning, they will know that. It's gaining quite a lot of traction because neural models alone can make very funny predictions. They can be very confident about very wrong predictions, or they cannot incorporate more generally common sense constraints. So for instance, in autonomous driving, they can predict a traffic light to be both green and red at the same time. Not to mention more complicated constraints and physical constraints or anything. So using neurosymbolic learning, you can add common sense constraints and reasoning to the problem, directly in the loss function. How do you plug in epistemic uncertainty in neurosymbolic AI? This is the project, the aim of this future project. Okay, this is it from me. The project received funding, like I said, from the EU Horizon 2020 framework. Thanks for your attention. This was just a brief introduction, but if you want to know more about what we do in the EPI project, please come to me. I'm not sure we have any time for questions at all, so maybe we want to move. We have a little bit of magic with, coffee breaks and lunch breaks, but, we don't want to eat into them too much. So unless there are questions, we'll just move on to the first invited. Yeah.
Thanks for you, and I'm honored and my pleasure to introduce our next speaker, Professor Epistemic from Carnegie University. Because of the time, we just make it short here. The stage is for you, please.
Okay, I think you can hear me. So let me try and share my screen. Which doesn't seem to work.
He's on the other end here.
Yes.
Just a second.
Might be the second screen. Move your first screen onto the second screen.
Just a second, please.
He's getting there.
I think that I have to.
Start. Yeah. I saw the message you started the Zoom.
Oh.
Hope to see you again.
Can't reach through. We'll be back.
Yeah. Yes, yes. Yes.
Yeah, I'm back, but all right. There was I don't often use Zoom, so I'm at a loss. I'll try to share my screen now. Where is it? Okay, can you see my screen?
Yes, yes, yes.
All right. So you should be seeing imprecision and why it is useful.
Yes. Yes.
Yes.
Oh, right. Then I can get started. Fine. So as the title announces, I'm going to talk about imprecision in probability theory and mostly why it is useful. Now, 20 minutes is a bit short to give a very general appraisal of why imprecision can be useful. If you want to learn more, I think there's a number of presentations on the SIPTA website, the Society for Imprecise Probabilities, Theories and Applications, where you can find out more. But I'll try to do my best and convey to you in about 20 minutes why I think that using imprecision in imprecise probability, in probability theory is useful. And I'll start with a very simple case, the basic case, and that is probability intervals. So what we have is what we call a possibility space, the outcome space for a certain experiment, if you want, and an event is then a subset of that possibility space. And we are going to specify a lower and an upper bound for the probability of that event. So the lower bound is a lower probability of A, the upper bound is the upper probability of A. We can do this because we have no idea about the actual probability of A, or because we simply do not want to be more specific. There are many reasons why we could want to be imprecise about this probability of the event A. In any case, it is a subinterval. This probability interval that you see here is a subinterval of the unit interval. And it becomes really interesting when we start adding other assessments, so other events and other probability bounds for those events. For instance, the event B here, depicted here. So we have another probability interval, a lower and upper probability for that event. And then we can start asking ourselves, for instance, what are, given the bounds that we have for the probability of A and the probability of B, what are the bounds that we can have for other events, such as, for instance, the probability of the intersection of A and B. So what are the implied bounds there? Now, in order to solve this problem, what we will do is we will assign possible probabilities alpha, beta, gamma, and delta to what we call the constituents. So those are the areas in the possibility space that are demarcated by the events A and B. So these are, in essence, probability mass functions. So they should sum to 1, and they should be non-negative, these alpha, beta, gamma, and delta. And of course, they should obey the bounds that we specified, in the sense that the sum of alpha and beta, which is the probability of A, should be between the specified bounds, and the sum of beta and gamma, which is the probability of B, should be between the specified bounds. And then we're interested in the probability of the intersection, which is actually beta. So we're interested in lower and upper bounds on beta, and what we recognize immediately is a linear programming problem. And if we solve that linear programming problem, then we get a simple solution, and it is known by the Boole-Cochet bounds. It is a problem that was first considered by Boole in his logic of chance. So this is, well, I mentioned this very simple problem to you because actually it is indicative of a much more general approach. And the idea that I want to draw from that is the following, that if I specify bounds on probabilities for certain events, then I can look at the set of all the probability measures that satisfy these bounds. And of course, such a set of probability measures will then be closed and convex. And so typically, and then I'll have to work with closed and convex sets of probability measures on the given possibility space. And I will call such a closed and convex set of probability measures a Creedle set. So one possible version is depicted here. Now, interestingly, once I have such a Creedle set, then I can look at other probabilities for events that haven't been satisfied or haven't been proposed yet. And I can look at the probability of for any event C, or the probability for any probability in the Creedle set. If I let P range over the Creedle set, then this probability will range over an interval that is completely characterized by its lower and its upper bound. And typically these upper and lower bounds can be found by linear programming problems. So that is fairly straightforward. Right, so this was an idea that was already envisaged by George Boole, but it turns out that in order to get a more complete language, we need to go a little bit further. Sorry, I'm going to continue because I couldn't understand what was said. I saw there was a question, but I'm not sure. So we have these expectation intervals. What am I going to do now? I'm going to show you why this isn't as complete and as nice as one would like, and that there are ways of making it better. So in order to do that, I will look at a very simple example of Sorry? So I keep hearing things, so I'm not sure if you want to tell me something or
Just in a
whether-
bit. Just in a
What?
bit.
Sorry, I don't get it. Sorry.
Background. I don't see any question. Please go ahead.
Ah, no, okay, because I keep hearing things in the background, and I was worried that there might be questions. So I will continue here. Right. So we have what I'm going to do now is look at the case not just where we have events, which are subsets of the possibility space, but also look at gambles. And gambles are essentially, mathematically speaking, they're just functions from the possibility space to the real numbers. Yeah. So I'm going to look at the special case of a possibility space, an outcome space for my experiment, whose outcome is uncertain, and there are three possible outcomes, A, B, and C. So let's look at this special case in order to get the meaning and as an example. Right, so a gamble is a real valued function on this space. It means that it's completely determined by the value that this function assumes in A, in B, and in C. So in other words, we have three possible real numbers, so I can represent any gamble as a point in a three-dimensional space, simply by specifying the coordinates as the values of the function. Yeah. So in this three-dimensional space, that's where the gambles on this possibility space live, special gambles are, of course, the probability mass functions, the precise probability models, because these are also functions on the possibility space, and they satisfy the requirements that they're non-negative, so they live in the first orthant, and they should sum to 1. So in this case, they lie on this blue triangle. So every point on this blue triangle is a precise probability mass function, and therefore what we call a precise probability model. Now I'll move this triangle to the right. So what you get here is this, what is called the probability simplex in 3 dimensions. Any point in this probability simplex represents a precise probability model, a precise probability mass function. And so, for instance, this point that you see here, the probability of the event A is the distance of this point to the opposing side. So A is here, the opposing side is here. So this is the probability of A. And then this is the probability of C. And this is the probability of B. And these add to 1. So any point in there is a precise probability model. Now, if I specify the probability of A, say the probability is 1/2, that means that I'm selecting all the points on the line that lie at a distance 1/2 to this opposing side here. So this is the line of all the possible probability models, precise probability models that correspond to this statement. For another statement, I have the probability of A is 0.2. So these are all the points that correspond to that. If I take 0.5 as an upper bound and 0.2 as a lower bound, and what I have, is all the points in this blue area are now all the precise probability models that satisfy the constraint that the upper probability is 0.5 and the lower probability is 0.2. And of course, I can do that for other events like probability of B and the probability of C. And in this case, when I do that, and I put all of them together, I take the intersection of all these areas, and the blue area now gives you the point of all the precise models that correspond to the constraint. So this is the corresponding Creedle set. Now this Creedle set has the interesting property, and it is always the case in such examples, has the interesting property that the sides of this Creedle set are in fact parallel to the sides of the simplex. Yeah. And this always happens in all cases when I represent my Creedle set using bounds on probabilities. So if I want to get other Creedle sets whose boundaries are not parallel to the sides of the simplex, I need to do something else than specify bounds on probabilities. And what I in fact need to do is I need to specify bounds on the expectations of gambles. Because if I do that, I can get constraints or bounds or boundaries that are not parallel to the sides of the simplex. For instance, if I look at the gamble, I'm not sure you can see it well, but this is the gamble, the indicator of C minus the indicator of B. So this is a gamble that assumes 1 in C, 0 in A, and -1 in B. So it's a 3-value gamble. And expressing that its expectation is 0 is actually, if I do that, if I impose that, then I get this line of possible corresponding probability models. There's another gamble here. There's the indicator of C minus 3 times the indicator of B. It expresses that the probability, if this expectation is 0, this expresses that the probability of C is 3 times the probability of B, and that corresponds to all the precise probabilities on this line. I can also use this as lower and upper bounds, and then I get a Creedle set whose sides are not parallel to the sides of the simplex. So I can get all kinds of Creedle sets in that case. So I lose the restriction that my Creedle set is a convex polytope whose sides are parallel to the side of the simplex. So the idea or the upshot of this is that in order to get a really complete theory of imprecise probabilities, I need to also move away from probabilities and move to expectations of functions, expectations of what we call gambles. Now, the idea then, in a nutshell, is that we start with an assessment of lower and upper expectations for certain gambles. You give me a number of gambles and lower and upper bounds on those gambles. What we do is we look at the corresponding Creedle set. That means the set of all the precise probability measures that satisfy these bounds, lower and upper bounds. And once we have the Creedle set, we can then look at any gamble, not necessarily one in the assessment, but any gamble. And then we can look at the expectation of that gamble for every probability in the Creedle set. These will range over an interval that is completely characterized by a lower bound and an upper bound. And if we can find that lower bound and upper bound, then we have what actually done, and this is important, what we've done is we've done conservative inference. We've used certain bounds on the probabilities and the expectations of certain events and gambles to infer conservative bounds on the expectations of other gambles. And this is an idea that was already present in Boole's work and was taken and was given extra importance in Peter Woolley's work, and this idea of conservative inference. So this tells us that actually behind probability theory and behind this type of arguments, there is a logic, a type of inference, an inference mechanism hiding behind all these things. And we can bring that inference mechanism to the fore by looking at the notion of what are called desirable gambles. The idea is very simple. As I said, a gamble is just a function from the possibility space to the real numbers. You can interpret it as an uncertain reward. So I don't know what element of the possibility space will be the outcome of my experiment. So if I take a gamble, if I take a function, then the value of that function, which can be interpreted as a reward, is also unknown or uncertain. So the value of the gamble in the outcome of my experiment is an uncertain reward. You can express that in terms of dollars or terms of other types of utility. And then you can ask yourself, would I prefer engaging in that gamble, getting that uncertain reward, to the zero gamble, to the status quo? And when you do, when you strictly prefer this outcome, this uncertain outcome, to the zero gamble, to the status quo, then we call that gamble desirable. Yeah. And then the idea is that there is a logic of desirability that is based on elementary statements. Statements of the type, the gamble F is desirable, where F can be any gamble on the possibility space. And this is represented by this simple symbol that says F is desirable. And then we have very simple desirability axioms. The first axiom says that zero itself is not desirable because you can't strictly prefer 0 to 0. Yeah, so very simple. So this is the contradiction or the destructive axiom, if you want. Then we have constructive axioms in the sense that if a gamble is positive and not 0, if it's not actually 0 and everywhere positive, so you can't lose from that gamble, then you must find it desirable. If two gambles are desirable, then their sum should also be desirable. And if a gamble is desirable, then multiplying that gamble with any positive number should also be desirable. So these are four very simple axioms, very much like propositional logic. And it turns out that if you can do a very simple type of logic with that, and the results are the notion of conservative inference associated with that. And that conservative inference is actually a logic that lies behind all of probability theory. Yeah? In fact, all of finitary probability theory, because I'm not assuming any continuity axioms at this point, but you can also do that if you want. So what we have is this very simple 4-axiom type of logic underlies all of probability theory. In fact, you can define lower expectations for any gamble in this way. So the supremum alpha for which F minus alpha is desirable is then a lower expectation. You can get upper expectations. When they coincide, you can go to expectations. You can go to probabilities in this way. You can actually also do conditioning in this way by looking at gambles that are called off, that are multiplied by an indicator. And this, in fact, leads you to Bayes' rule. So also Bayes' rule is part of this logic and is therefore also, in a sense, deductive. So this is the message that if we allow for imprecision, what we uncover, what we are allowed to see at that point is that this lays bare the conservative inference mechanism that lies behind all of probabilistic reasoning. And I think this is an important message. One of the reasons why I think that allowing for imprecision and allowing for imprecise statements like of this type, that this shows that there is a logic and a conservative inference mechanism behind probability theory. Okay. There's something more I wanted to tell you. So another advantage of using imprecision in imprecise probabilities, so in probability theory. And that comes to the fore when we look at stochastic process. So let me briefly give you a crash course in stochastic processes and imprecision there. A stochastic process is just a sequence, a timed sequence, if you want, of random variables, variables whose outcome is uncertain. So you have a variable at time 1, at time 2, at time 3. So the index represents the time. I'll look at the very simple case, just as an example here. I look at the very simple case of a stochastic process with 2 possible outcomes, 0 and 1. Coin flip, if you want, or a sequence of coin flips. Yeah. So we can represent this, all of these possible outcomes, all these possible realizations of this process, we can represent this in what is called an event tree. So start with nothing, then I get either a 0 or a 1, and then if it's a 1, I get either a 1 or a 0, and so on. So I can find all the possible realizations, I can represent them in this event tree. And every node in this tree is a string of 0s and 1s, and I will call such a string a situation. So a node is a situation. It's just a finite sequence of 0s and 1s in this tree. If I go on forever, then eventually I come up with a potentially infinite string of states, and that is typically called a path in this event tree. Okay. We haven't said anything about uncertainty yet. So now I'm going to add uncertainty and get to what is called a stochastic process. So how do we do that? Well, typically what we do is in each of the situations, we will define a local probability mass function. Why is it called local? Well, because there is one in each of the situations. And the probability mass function is actually about the outcome of the next step. So if I'm after observing a 1 for the next step, I can observe a 1 or a 0, so I can go to one of these 2 children, and the probability for that is governed by this mass function on 1 and 0. So a very simple local mass function. And I can do that in each of these situations. And when I do that, we get what we call a probability tree, and that is equivalent to a stochastic process. So that's a precise probability tree. How do we get to an imprecise probability tree or an imprecise stochastic process, if you want? Well, simply replace all the local precise models by local imprecise models. So we associate now a Creedle set, a convex closed subset of probability mass functions to each of these situations. What's the interpretation? Well, the interpretation is very simple. With each imprecise stochastic process, so the one that you see, the one that you see depicted here. Let me go back here. The one that you see depicted here, we can associate an infinity of precise stochastic process. Simply what we do is, in each of the situations, you choose a precise mass function in the set that is available there. So you choose one in the set for each situation. And of course, you can do that in an infinite number of ways. And what you see, in fact, is that if you go further in time, this increase in complexity is exponential, right? So there are infinitely many, and they increase exponentially as time goes on. This means that, so how do we reason in these imprecise probabilistic stochastic processes? Well, typically what you do is you do the inference that needs to be done in each of the compatible precise models, and then you take the range over all the values that you get, and that range gives you the result of your conservative inference. So it's very, very easy to see that this is incredibly complicated, right? But the idea is that an imprecise probability tree or an imprecise stochastic process is just equivalent to a set of precise probability trees. And that allows us to link, and that is another bonus, I think, of this approach. It allows us to link this, this measure theoretic probability tree that is typically used in stochastic processes to an approach to probability tree that is advanced by Glenn Schaefer and by Volodya Vovk, which is a game theoretic probabilities. So this, what I've told you now, is exactly the link between these two approaches. Right. So working in general with imprecise stochastic processes is very difficult, computationally very complex, but not always. There are cases when that is not so, when it's not so complex. And for instance, one of these cases is when we look at imprecise Markov chains. So what are imprecise Markov chains? These are chains where the local models, which are Creedle sets, so the local Creedle sets satisfy a Markov condition. Markov condition says that the model in a situation somewhere only depends on the last outcome, only depends on xn's. For instance, the model here in 1, 0 should be the same as the model here, because the last outcome is a 0. So the model here must be the same as the model here. In that case, we have what is called a Markov condition, and it turns out that many inferences in such what are called imprecise Markov chains are no longer exponential in complexity, but become polynomial in complexity as a function of time. Yeah. So they are very easy, very simple. And so what does this tell us? It tells us that, and this is interesting, and I'll tell you why it's interesting, because if you look at these compatible, so I have this Markov chain here, this imprecise Markov chain, which is, as I told you, an infinity, which it's an infinity of precise stochastic processes. And amongst these precise stochastic processes, there are processes that are not necessarily Markov. Because here I must choose a model, and here I must choose a model. The set of probabilities that I can choose from is the same because of the Markov condition, but the precise model that I choose need not be the same. So in other words, that compatible stochastic process need not be Markov. Yeah? So what am I doing? I'm replacing a non-Markov system by something that is more imprecise, that satisfies the Markov condition, and where calculations are polynomial in complexity. So if I start with a very complicated, precise stochastic process that I can bound by a Markov chain that is imprecise, then it's possible that whereas the original precise stochastic process was very difficult to deal with and computationally very complex, I can approximate it conservatively and very often with very good bounds by something that is computationally tractable. And that is something that I want to stress here by looking at this triad. There's a triad between accuracy, precision, and simplicity. Accuracy means that your model is correct. Precision means that your model is precise, that it gives precise numbers. Yeah? So we can lose precision by going to imprecise numbers, and then we can still remain accurate by making sure that our intervals here cover the actual model. Then we're still accurate. But of course, this is we lose precision. Now, this is, of course, the standard trade-off. This is not very new, but what we see now is that there is an additional factor that needs to be taken into account, and that is simplicity. It is possible that we have a very accurate model that is computationally very complex, and that is therefore impossible to evaluate. We can still remain accuracy by becoming more and more imprecise, and we can become imprecise in such a way that the bounds, the conservative bounds that we get to, become computationally simpler than dealing with the accurate, precise model. And therefore, in order to look at the trade-off between accuracy, precision, and simplicity, we get something that is interesting and new. And this is another advantage of dealing with imprecision in probability theory. Okay, in summary, what I tried to, what the message I try to give here is that, first of all, if we allow for imprecision in probability theory, this will allow us and help us to identify and to exploit the logic and the conservative inference mechanisms that lie behind probabilistic inference, behind probabilistic reasoning. It provides a natural link between measure theoretic probability and game theoretic probability. On the other hand, it allows us to use more conservative models that are computationally more tractable to deal with difficult and computationally intractable precise derivations. And finally, I think this is also important, I think it allows us to do away with the distinction between so-called epistemic and aleatory uncertainty. Because even if we allow or admit that there is something like aleatory uncertainty, and that even if we admit, which is not necessary, but we could admit it, that this aleatory uncertainty is precise, even then this aleatory uncertainty must satisfy the logic behind probabilistic reasoning, and can therefore be approximated usefully using imprecise probability models in very much the same way as epistemic probability this is possible in very much the same way for epistemic probability. So the distinction between epistemic and aleatory goes away if we start looking at imprecise probability models. That's the message that I wanted to convey, and I'm happy to answer questions if there are any.
Any questions?
I heard Fabio here.
Hi.
How are you?
Okay.
I mean, your slide on the stochastic processes sounds very relevant to the work we are trying to do in reinforcement learning. I know you've done some work on imprecise graphical models, haven't you, in the past?
Yes, yeah. Also, Bayesian networks, of which, of course, Markov chains are a very special case. Yeah. There's some work done there.
Applying those ideas to reinforcement learning, or are you aware of any recent work in that area?
Well, dealing with what we call imprecise Markov chains is in fact equivalent to, but it's another way of looking at the same problems that Markov decision processes do. But so in Markov decision processes, you look at actually at the process that or at the policy that gets you there. Whereas what we do is we look at the bounds that are generated by those policies. So it's a different point of view, but it turns out that if you, and so since Markov decision processes are also formally equivalent to things in reinforcement learning, I think that the algorithms that we've developed can be useful in those problems as well, and vice versa, because there are algorithms in reinforcement learning and in Markov decision processes that can be used to do what we need to do as well. So there's, I think, a fruitful exchange between these fields, yes.
Maybe we can have a conversation offline about these things.
Sure, yeah.
Thank you.
Thank you for your inspiring lecture. I'm just wondering if this theory can be extended to stochastic processes with a continuous index, like continuous time, rather than Markov chain. Like, does it work?
Yes, it
Can
can.
it be extended to this type of stochastic process? Question.
Yes, it can. It can actually. Yeah, there's a budding research field where this is done, and this is also there are also links with financial theory where these nonlinear, these are typically groups of nonlinear propagation operators that you're considering at that point, and so there are links between functional analysis, operator theory, nonlinear operator theory, and these continuous time imprecise stochastic processes. Yes, there are results there.
We get some references from you, like links to some references on this topic. I mean, in precision in this continuous time stochastic processes. So literature on this, or some links or suggestions where to start reading on this.
Okay. Yes. Well, if you probably have my email. If you send me an email, I can, because there's a lot of references that I can give. So I will answer your email and send you a few references if you want them. Is that okay? Yeah.
Any other questions? Not yet. I have just one maybe stupid question, because I read a couple of papers, especially using Creedal sets in machine learning. And in some of the papers, I saw many notations, many new names, which was confused me, but took time to understand what is really those notations compared to what we have from Peter Molyneux's. The definition of Creedal set in some papers I read clearly telling that the sets of distributions. And I think this is not in general correct. What we also see in your presentation, nice presentation, the definition of Creedal sets in general, what we saw in the slides. Am I right here? Because the sets of distributions, cumulative distributions in general, it's called P probability box, which could be a special case of Creedal sets.
Yeah, it depends on what you mean by distribution. You could mean a cumulative distribution function, or you can mean a density function, or you can mean a probability measure that it's a distribution. But there is in the literature there's a lot of confusion about this term distribution, I think. But typically, a Creedal set is a set of probability measures, right? And so specifying a set of densities is not necessarily the same as specifying specifying a set of distribution functions is the same as specifying a set of measures, of course. But specifying bounds on distribution functions is not the same as specifying bounds on probabilities in general. So you get weaker and weaker models if you go to, for instance, what is called a p-box. Then you get a set of distribution functions or bounds on distribution functions, and that is weaker, a less strong model, a less, how shall I say, a less potent model, if you want, than general sets of probability measures. Yes.
Great. Thanks, Gert.
Yeah.
Okay, if there is no more questions, we go to the first coffee break. And then we come back at 10, please. Thank you.
Thank you.
Yeah, if there was let's say.
Yeah.
Unless they ask not, so then we will have. Okay.
Yeah, you still have to hear it. So.
Yeah, and they.
I don't hear it either. No, we don't share. We'll hear it. So we have to go to Zoom.
Okay.
Yeah, I'm leaving my.
Okay. I have this free one for a second.
Free flip on it. Yeah, you know, free. That's it. Yeah. We need to hit pop music. Sounds. I'm just that might not make a big cover and it's. I'm sorry. Think of that. That's let's see. You could be hearing it in the room. Testing.
Approach. This approach does not require modification of the deployed neural network and guarantees
Unmute.
the defensive perception envelope has the capability to estimate the neural network's performance and is extended by novel methods to reduce computational effort. Here is system flow overview. Since the perception stack is trained for only one source domain or specific source domains, the defensive perception envelope informs the system if an unknown domain was entered. Our metrics that we used to estimate that uncertainty. And as already mentioned, we use the Monte Carlo dropout approach, which means we have multiple forward passes with the same input data and the same model, but we insert a dropout layer, which and that allows us to have the possibility to have different predictions for the same input data. We then try to measure the difference with the pseudo-cross entropy metric that is written down here. The advantages of this matrix are it is independent from the number of forward passes, it depicts the entropy emerging from multiple forward passes, and it smooths the uncertainty for small deviations while upscaling larger ones. Our first experiment was with the MNIST dataset. The MNIST dataset, I'm sure you all know it, is the dataset with handwritten numbers where you have to predict the number from the image. The model was trained on the standard dataset, so the numbers were not rotated, but for the test set, the numbers were rotated anti-clockwise up to 90 degrees in 10-degree steps. Then the uncertainty was calculated with our new uncertainty metric using 20 forward passes, so 20 predictions per number, and with a dropout rate of 0.4. Also, the error was calculated to compare our uncertainty metric, and we also looked at the maximal number from the one-hot vector. If we now look
Okay, stop. And then start again. Save. And then it is this. All right, let's share.
Let's give out, I'll share. That is so. This again. Let's stop it. Where is that?
The video. It's cool.
Okay. Stop it. So go back here. All right. So let's go share again. Put sound and video.
Mhm.
Share. Okay. That's it. Good.
Um,
You got it there.
approach. This approach does not require modification of the deployed neural network and guarantees expected model performance. The defensive perception envelope has the capability to estimate the neural network's performance and is. My name is Stefan Bühler, and welcome to our poster presentation about our paper Defensive Perception, Estimation and Monitoring of Neural Network Performance under Deployment. In autonomous driving, it is crucial to know if an autonomous vehicle left the operational design domain and in general anticipate uncertainty of the perception system. In this paper, we propose to address this by encapsulating the model within an uncertainty estimation envelope that is based on the Monte Carlo dropout approach. This approach does not require modification of the deployed neural network and guarantees expected model performance. The defensive perception envelope has the capability to estimate the neural network's performance and is extended by novel methods to reduce computational effort. Here you can see the system flow overview. Since the perception stack is trained for only one source domain or specific source domains, the defensive perception envelope informs the system if an unknown domain was entered. Uncertainty arises. At the top here, you can see our metrics that we used to estimate uncertainty.
Well, that's it.
As already mentioned, we use the Monte Carlo dropout approach.
Yeah, I mean, they're talking back and forth. They're talking.
Have multiple
things to each other. I mean, I was like, I can hear it
with the same input data,
because
the
if
same model.
you plug this in, it's
We
still outputting the
insert
direction
a
on
dropout
there.
layer, which this and that allows us to have the possibility to have
Wait a minute.
different predictions for the same input data. We then try to measure the difference of these predictions with the pseudo-cross entropy metric that is written down here. The advantages of these metrics are it is independent from the number of forward passes, it depicts the entropy emerging from multiple forward passes, and it smoothes the uncertainty for small deviations while upscaling larger ones. Our first experiment was with the MNIST dataset. The MNIST dataset, I'm sure you all know it, is the dataset with handwritten numbers where you have to predict the number from the image. The model was trained on the standard dataset, so the numbers were not rotated, but for the test set, the numbers were rotated anti-clockwise up to 90 degrees in 10-degree steps. Then the uncertainty was calculated. with our new uncertainty metric using 24 passes, so 20 predictions per number, and with a dropout rate of 0.4. Also, the error was calculated to compare our uncertainty metric, and we also looked at the maximal number from the one-hot vector. If we now look into this graph, we can see that the maximal one-hot number nearly drops, while our uncertainty value increases down here, up to about 0.4. Yeah, if you want to do this experiment yourself, you can follow this QR code here and you will find a notebook where you can find the code for that. Now, coming to an autonomous driving problem, we have switched over to a data set that uses semantic segmentation on street images. And yeah, the first experiment we did was to train a model only on day images, so on the day domain, and then switch the model over to the night domain. So use the same model that was trained only on day images on night images. And then we want to see if we can use our approach to see the uncertainty within the model.
Oh,
in the
Monday.
first image, you can see the input images.
Monday I had my own laptop.
Images.
I'm figuring out what's I was.
In the second image, you can see one model prediction. Of course, there are more predictions for the
Work one. Use the third one, and I'm wondering.
My name is Stefan Bülow, and welcome to our poster presentation about our paper, Defensive Perception. Hello, my name is Stefan Bülow, and welcome to our...
I technically shouldn't be connected. You're hearing yourself, yes. That's the best thing you can do. You're talking about. He was talking about this. Let's see if we can do it. Leave computer audio. We're still sharing with audio.
Our poster presentation about our paper, Defensive Perception, Estimation and Monitoring of Neural Network Performance under Deployment. In autonomous driving, it is crucial to know if an
Yeah, you kind of have to balance it because yes. Yeah. I can explain it. So we're going to turn this one down and get ourselves. So we'll kind of have you balance now.
What is the guy?
About our paper, Defensive Perception, Estimation and Monitoring of Neural Network Performance under Deployment. In autonomous driving, it is crucial to know if an autonomous...
You can hear me on Zoom. Exactly. You can hear me. You hear all that on Zoom.
Sorry.
And then it's on the feed. But we're not hearing ourselves after the machine.
AB, yeah. About it,
Yeah, this is how they- so-
No, we're just talking about.
You understand? It seems I didn't change anything.
So it's good.
We're good.
So just, you know,
What's
this
this
is the
first up?
posters, if
No.
anybody asks. Okay, I try to find the organizer.
Yeah.
But you want to know? Right.
Well, there's a
What's
schedule
the
shared.
step?
Yeah, they changed it all.
Yeah. What's up, right?
I mean, we know what to do now, so we're good. Yeah, you stopped. You probably have other screen shares to go. We're good, I think. Well, you wanna. Get back to money. Can you please make the image sharper? Shoutful.
I mean, yeah,
It's pre-recorded. Yeah, it should be on his laptop. It should be on his laptop.
Like I didn't say it.
Oh, you didn't send him anything?
Oh, he didn't.
Oh, good lord. Okay, so,
Don't worry.
yes, please. Yes, please. And then we'll have him open up on his laptop. Yes, yeah, thank God. I thought everything was supposed to be on, well, never mind. It hasn't been all week, so. We'll be fine. We find, Kevin.
You know, she wrote that.
I do, oh, yes, I do. Yes, I did. So, let's keep on. See that? We're good. That's all. I'm trying to make this bigger. We're gonna ask this to be sharp. Yeah, it's pre-recorded. I don't know if I can make that sharper. Bigger. Oh, that's supposed to be. No, that would be enough. That would be enough. Yeah, it's pre-recorded. So. You said you were next. You're the next one up. Okay. We can come back here. Lower that up. Yes.
Recording in progress.
Please mute yourself if you don't have any. Gentlemen, yes, and invitation. Yes.
Give me email. Okay. Yes. Okay. Yes. Okay, our next speaker is Michael. He will give us talk about the representation of learning benchmark for transferable uncertainty estimation. Please.
All right, yeah, thank you so much for making the workshop and bringing this small community together. I'm going to talk a bit about bringing communities together too, and that is bringing our community to the general machine learning audience. And so I'm going to talk about pre-trained models and how we can bring our amazing uncertainty stuff to the general public. A quick introduction into representation learning, in case you are not familiar with it. Representation learning is a big thing in the last years in the machine learning community. And what people are doing is they're taking images and then they're training an encoder to place that image into some kind of latent space. And the whole idea is to have the latent space represent the similarity of the images. So similar images are put closely in the embedding space, and we can use that for downstream tasks to just get a jump start at our task. And one thing that these people have not yet thought of is what happens if an image is ambiguous. So it could be that the image is blurry or has a low resolution. And sure, the model will still try to put it somewhere in the embedding space. But actually, it could be anywhere, right? We don't know if this is like a horse or a cow or an animal at all. So while we should still present an embedding that we can use for our downstream stuff, we should also have some notion of saying we're not quite sure what this actually is. In other words, what we're trying to do is to output both an embedding and an uncertainty estimate for every pre-trained model that we use. And the reason for that is very simple. It takes a lot of data to train uncertainties on downstream tasks, and we often don't have that. But if we do that for our pre-trained model, and if we already train a general notion of detecting uncertainty, we will need less data. People can use it like in normal pre-trained models, it will accelerate the research. And another thing is just, it makes it much more convenient. So imagine you have a model, you want to have uncertainties, and you're like, oh, this is like a big task, I better not do it. But then we just say, well, you can just download our pre-trained weights for your ResNet, and we're just going to give you the uncertainties. You can have them. That's probably going to work quite well. I've talked to quite some people in the last few weeks in the conferences, and they were all like, well, yeah, the American way to say it was, if it's free, it's for me. So that should be our task. We should be trying to give these people the uncertainty estimates, and they can use them for whatever they want to have. And the big task towards developing such a good model is always to define a nice numerical benchmark where we can develop along and iteratively improve our models. So the goal of this paper is really to propose a benchmark for pre-trained uncertainty estimates. And the big question to me and my supervisors was, how can we define a metric that captures the if the uncertainty over a latent space is actually the correct uncertainty we want to have. So let's try to explain our metric and our benchmark in like 3 slides. Let's actually start with normal classification. So if you have normal classification, you're just going to output some kind of class and some kind of uncertainty estimate U. Could be a probability, could be also just an arbitrary scalar value. And the cool thing is, and the key insight behind this paper is, uncertainty estimation is from a decision theory perspective, the same thing as risk prediction. So what we're going to do is, if we provide a prediction of a class, and we are saying, but we're not certain about this, then what we're meaning is we expect a high loss if we do this prediction. So all we can do in classification is to just give a calculate our accuracy on that class, and to evaluate the uncertainty estimate, we're just going to see if this uncertainty estimate can predict whether this accuracy will be 1 or 0, the loss that we use in this case. If you have any questions, interrupt me at any point. So with this paradigm, we can do the same for representation learning. In representation learning, we also output some kind of uncertainty estimate. I leave it open what that is in particular. And we output some kind of embedding. And now the way that the loss that the people use in representation learning is the recall at once. That just means you embed all of your data, and you just see if your data point, if your test point is embedded as a next neighbor to a point in the same class or not. It's quite similar to classification, but it does not need the class label at train time. That's why they do it this way. But for us, what's important is this is still just a 0-1 loss, like in classification. And so just like in classification, we can just evaluate if our uncertainty estimate is proportional to that loss, if it can predict whether the recall at 1 at this point will be 0 or 1. And so then we have some kind of scalar value u, and we want to see if it's predictable some binary value that is like a 0 or 1. What we can do is we can just calculate the OROC and the area under the ROC curve. We're just going to call it R OROC here because it's the recall at 1 OROC. And that's really everything that there is to this metric. Maybe one more word about why we are trying to do this. Every time you have some kind of encoder model, you basically have an information bottleneck, right? You start from X, you go to your embedding, and then you go to the label Y. And so as soon as you have uncertainties in the embedding E, which is what we're trying to measure here, you will have uncertainties in your target label Y. So that's why it's super important to already represent the uncertainty at the embedding space. And here's the same as a code thing. So I just took some general representation learning benchmark code, which essentially embeds all the data, then calculates the recall at 1. And really all we have to add is one line of code. We just have to see if our predicted uncertainties are proportional to not having the same class, i.e. the recall at 1 being 0 or 1. That's everything we have to add to the code. If you're too lazy to add this yourself, we also have code online. You can use our code. I'm going to come to that later. Okay, and then I said we want to have pre-trained models. So pre-trained models, we want to basically always transfer to downstream tasks. So what we're doing here is we are pre-training on ImageNet 1K, and then we are evaluating this ROROC and also the traditional recall at 1 on some downstream tasks that are zero-shot, like CUP 200, CARS 196, sample online products, just to see how it performs on novel tasks. And that's the whole benchmark. If you have questions so far, please raise your hand. Yeah, sure.
I want to know, like, this seems a little restricted to me to use this recall at 1 metric. So, for example, I mean, you lose a little of information, right? Sorry. Yeah, sorry. So I just want to know, like, it feels to me like you lose a lot of information when you use that recall at 1 metric. So, for example, you could also use something like the minimum distance to the next neighbor, which is of the same class, something like that. So, is there a rationale behind using this metric in particular?
That's a good question. The main rationale is that the recall at 1 is the most popular thing in representation learning. So we're really trying to build an adapter that can be easily added to representation learning. As soon as you define a different loss function, you can still just measure if the u of x is proportional to that specific loss function. So if you want to personalize it to your case, just try the same, try to see if it predicts the loss.
Okay, thanks.
Thank you for the question. All right, otherwise I'll go in and let's see what we actually found. The main questions that we had is, well, of course, the first question is what of the current methods in the literature give us the best transferable uncertainty estimates? And the second question we were trying to answer is, that's a very common question or common grudge that people have towards uncertainty estimation is, will it make my main task worse? Is there a trade-off between uncertainty and recall? And the third question is, if you're still skeptical to the metric, we also just wanted to see if this very technical metric actually corresponds to human notions of uncertainty. So let's get started. Here's the stuff that we implemented. We re-implemented everything. We trained everything under the same fair conditions, hyperparameter tuned everything. The first broad category of recent methods is probabilistic embeddings. So these methods use different loss functions like MCInfo, NCE, ELK, and EBMF, ITCH, and HEADXL, all published in the last 2 years. Their goal is to just predict both a mean and a variance, and then have a distribution of the embedding space to represent the uncertainty. It's kind of like a VAE, but it's only training the encoder using those losses. The second category of models was just risk modeling, so they just directly try to predict the variance. In terms of risk spread, that's a very simple approach. It just tries to regress the loss directly, also having this kind of decision theoretical notion behind it. Third category is ensembles. I bet you know them. They just train different heads and then see what the variance is. And then we also just had baselines, like what if you just use your normal, what if you just let's see. All right, don't worry. So the fourth one is just baseline. So we just looked at what happens if you train with a normal cross entropy loss and just use the upstream class probabilities of the ImageNet classes and the entropy of that to detect uncertain samples, or the same for info NCE, what if you use the embedding norm. And here's the results. This is the recall at one at those downstream data sets. And I'm not going to go too detailed about this for time reasons, but the big thing we can see is probabilistic embedding approaches are very good. They're among the best methods here, and also among the best methods for VITs. We trained on ResNets and VITs. I didn't mention that before. And also this risk prediction approach, or SNGP, they're also quite good, especially for VITs. So these seem to be kind of the ways to go. What didn't work was ensembles, because they're trying to measure epistemic uncertainty, while we are more interested in the aleatoric uncertainty here. And what also did not work was cross entropy. It just doesn't work to predict your upstream labels entropy if you have your downstream as a task. Yeah, so let's have this one first.
There's a question from the internet. Whoever Q is, can you unmute and talk to us? Yeah, Q can't hear us. He can actually unmute and talk to you if you want and ask this question.
There's a question up there.
Yes, we can talk.
That's all.
We don't hear you.
Not on here. Okay, so
Otherwise, go to the chat there.
yeah. So you want to? We'll have him read it. We'll have the gentleman here.
Cool. So QJ asks, are you assuming the pre-trained models output uncertainty?
Yes, we are. That's the big thing here. We benchmark pre-trained models that can output uncertainty. We can also make them output uncertainty. So the baselines I was talking about, the baselines we just use, like we just force them to output uncertainty, where we just use the entropy of the labels, for example. But there is like a category of models that also output uncertainties in various ways by construction. So usually they just have a second head that tries to predict some kind of variance or uncertainty. And that is still a pre-trained head. I hope that answers the question. Yeah.
Yeah. On that slide with the results that you have, well, we don't see now, but yeah, right. So you mentioned this risk modeling approach like SNGP doing really well, and I see that being the case on this fit medium, but actually on ResNet it seems to be among the worst. I wonder if you have any intuition on why this difference may be so big.
Yeah, it's a very good question. My main intuition, so you see this for that several results. Also for HEADXL, it's quite bad in ResNet, but quite good and actually very okay in bits. And also MC frequency switches performance, so it's kind of inconsistent. We currently believe it is because these methods were built for like very big amounts of data. So PET-XL and SNGP were proposed by Google. They trained on 4 billion images, and we're here training on ImageNet. And I talked to the Google people. They also said it doesn't work so well on pure data like on ImageNet 1K. It might be because these methods have a lot of parameters. PET-XL tries to parameterize like a 2000 dimensional Gaussian with a full covariance matrix. If you only have 1 million images, that might be a bit few. Yeah. That being said, my follow-up is to try to understand this better. Thank you for the question. All right. So those are the main results for the uncertainty estimation. Let's actually dig a bit more into detail. Now the uncertainty estimation, what we've seen before, is on the y-axis, and on the x-axis, we're also looking at the recall at one, so the normal retrieval performance and representation learning. And what we can see here is, well, first of all, I ran every approach 3 times, so I just plotted the bare, like the absolute raw data. So you can see 3 points for each approach. Big means VIT, small means ResNet. And one of the coolest things you can see is there is an approach that is very good in both of these metrics simultaneously. And that is risk prediction. So that's what I was talking about before. The very simple approach of just adding a head that tries to regress the detached loss. That's a very simple thing, and it's also a very stable thing. I suppose it is because it does not get an interference between trying to estimate the prediction and trying like the recall and trying to estimate the uncertainty. These are the two very clearly split things here. So it might be that generalizes very well. And so you could say there is not necessarily a trade-off between uncertainty and recall, but if you actually look into each model class, what we've done before is we've hyperparameter tuned them with respect to the uncertainty, being very good at the uncertainty. Now, in this case, we've tuned them in order to be very good at the recall. And now within each model class, we can look at the best models for uncertainty and for recall. And there we do see some trade-offs. Like within one model class, you can make models good for one or the other. In some cases, the trade-off is like quite drastic. So I would say that the question if there is a trade-off between uncertainty and recall is still up to debate, and also depends on the very loss you use. Some losses have it, some losses have one model that's best for both, and some, like globally seen, as we've seen before, some models are also just good in both. So it's still up to debate. And then the third question that we had was, is our technical metric recall or of any use? And this was actually the slide that motivated my whole research. So I was sitting with my supervisors and trying to search for good metrics and trying this out. What we tried out here is there are some data sets. These are new data sets. These are not the same 3 as before. These are 5 normal data sets. On these data sets, there is a recent paper that collected around 50 annotations for each image. And then if you look at the 50 labels, they will differ if the image is weird or ambiguous. So you can just calculate the entropy of the distribution to get an estimate of like how uncertain humans are about an image. And then what we did here is, for every model that we trained, we tracked the recall at one, our aura, and we also tracked this how well the model is aligned with those human uncertainties. And what we see is models that are good with respect to our metric are also good with respect to the human metric. So they behave, their uncertainties behave like human uncertainties. This is for us a reason to say that the recall might be a very good proxy objective to tune for that. We can also deploy in any data set if we don't have 50 labels per image. That being said, in the paper, there's a ton of more analyses. There's also correlations between every possible target value, which is quite interesting. Just look into the paper if you want to see more plots. A lot of plots there, much colors. And the last thing I wanted to point out is, you've seen this plot before. One last thing that we tried out is, okay, these are all 0-shot models. What happens if we actually train a many-shot model on the downstream tasks directly? And there we can see that these, just to get a gauge of like how good we can get in uncertainties, we can actually get like an aura close to 0.7 if we directly train a ResNet on the downstream data. So this gap here is pretty much your task, and my task for the next years. If we can bridge that, then we can ship those pre-trained models to the customers, to the broader machine learning community. All right, so that was it already. The main point I want you to keep in mind is about me, about my PhD thesis, about this work. We want to have pre-trained models that output not only in embedding, but only in uncertainty. That's what it's all about. And in this work, we said, okay, we can evaluate this uncertainty by seeing if it is predictive of whether the embedding is going to be correct or not, like on a second level. And result-wise, we've seen that probabilistic embeddings and risk predictions seem to be good, but there's still a lot of work to do in the next years until we can ship this. You can find the paper and the implementation in this QR code. It is implemented based on the TIM library, if you know it. So if you have just any kind of idea of what you want to do, all of the ImageNet training, all of the models, ResNet, bits, beats, these, you call it, it's already implemented. You can just implement your loss function and try your idea out and see if it performs better and then publish the paper, I guess. I want to thank my collaborators. Balin is a master student of mine. He's a very amazing person. I bet you will hear more of him in the future, very frequently. And also my two supervisors and the DFG for funding this work. And you for listening. Thank you.
Thank you, Mikhail. If there is any questions.
Well, actually, I have a question. I'm wondering if you do fine tuning, can you fine tune the uncertainty estimates also? Not sure if you may have mentioned that already.
That's a very good question. We're doing this in 2 weeks.
Cool.
That's our big hope, that we can do that and that they will provide a better starting position than just a randomly initialized head. We will do it in 2 weeks. The results will probably be uploaded by September. I can notify you, or you can send me a mail if you like. But very good question.
Thanks.
Any other? Okay, if not, thanks for trying again and giving me a chance. I would also mention here Mikhail and the other authors got the best student paper for this nice work. So we will have the ceremony in the afternoon. So the next speaker is about joint modeling for uncertainty quantification, which will be which will be presented with Terry. You send it? Okay, just going to check. Maybe yes. Interesting. Okay, so. Yeah.
Okay, hello. So my name is Terry Ma, and I'm currently an undergraduate student at computer science at Georgia Tech. And I'll be here to present the following work on behalf of the authors who unfortunately cannot make it here today. So this work is named Joint Modeling for Uncertainty Quantification. It was led by Dr. Chunling Ji, and jointly worked together with his co-supervised PhD students, Mr. Dingley Gong and colleague Dr. Mei Ying Zhang. The team would like to thank the workshop committee and reviewers for giving this paper a very high rating and awarding the best paper award. So here's the outline of this talk. I will introduce the modeling approach and detail the inference for uncertainty and evaluate the proposed method on two typical uncertainty quantification problems. So to begin, I will talk about the importance and application of uncertainty quantification. There's two major types of uncertainty: aleatoric uncertainty and epistemic uncertainty. So roughly speaking, there are two major approaches for uncertainty quantification. There's a frequentist approach and Bayesian approaches. And some challenges are that we want to handle both types of uncertainty in a single model. We want easy model fitting and low cost inference, and we want the model to be scalable for high dimensional data. So aleatoric uncertainty captures the noise inherent to in observations and cannot be reduced even if more data were to be collected. There's two types of aleatoric uncertainty: homoscedastic uncertainty, which is constant for different inputs, and heteroscedastic uncertainty, which depends on the inputs. The second one is more challenging to estimate. There are several approaches to estimating aleatoric uncertainty, such as Bayesian methods, including Gaussian processes and variant problem-specified models, and generative adversarial network-based methods. Epistemic uncertainty captures input space, which is unexplored by training data and can be reduced with more data. which is also known as model uncertainty. Bayesian methods provides the most straightforward way to handle epistemic uncertainty, such as Gaussian processes and invariant Bayesian neural networks. As an alternative, some non-Bayesian approaches are easily incorporated with complex data, such as images. Some well-known ones are MC dropout and deep ensemble. So compared with previous works, our work has the following features. It is a single model approach, which does not require specified model structure or training blocks for different types of uncertainty. It has an implicit regression model with limited hyperparameters, easy training with the SGD style algorithm, and closed form posterior expression, which has low cost for inference. In a conventional regression model, the link function has two parts, which can be interpreted as the feature learning part, Wx, and a nonlinear function part, Fv. The link function bridges the input data xi to its corresponding response yi. In this work, we present an implicit model approach to build the nonlinear function. We directly model the joint distribution of z equals Wx and then infer the conditional distribution of Py given x, or the nonlinear function from the joint distribution. We name this strategy as joint and condition modeling trick and present how to utilize it to infer the conditional distribution when joint modeling xi with a Gaussian distribution and a GMM. So this is the joint and condition modeling trick under single Gaussian modeling. And then this is the joint and condition modeling trick under Gaussian mixture modeling. This gives us an explicit link function to bridge the response y and the input x, which looks like a Gaussian kernel regression. However, unlike conventional Gaussian kernel regression, we do not need to directly estimate the mean and covariance. We obtain them from the fitted Gaussian mixture model and a closed form formula. Now we discuss. This is the joint and modeling and condition modeling trick under Gaussian mixture modeling. This gives us an explicit function to bridge the response y and input x, which looks like a Gaussian kernel regression. However, unlike conventional Gaussian kernel regression, we do not need to directly estimate the mean and covariance. We obtain them from the fitted Gaussian mixture model with closed form. So next, we will discuss how to process the feature learning part, Wx. The goal of the feature learning part is to find a good low-dimensional representation of x, which describes output y. The method used in this work is the linear dimensionality reduction model with a projection matrix W. To alleviate the ambiguity in finding the projection matrix W, we constrain the W being a member of the stifled manifold. We designed the loss function for learning W as follows. Regression loss, which encourages low dimensional representation X, can better explain why. It is a negative log likelihood where P, yi given Wxi is predicted conditional distribution. The reconstruction loss, which encourages a low dimensional representation of X, still has enough information to reconstruct X, prevent trivial solutions of the dimension reduction model, and sparsity loss to increase the model interpretation, particularly when D is greater than. What is a bit challenging to learn the projection W while keeping its orthonormal constraint. Traditional SGD update cannot guarantee the orthonormal constraint. We need to extend the Euclidean SGD to the stifled manifold to ensure that the result of each update is still in the stifled manifold. The specific approach has two main processes. Projecting the Euclidean gradient onto the tangent space of the manifold and to transform the SGD-based position update onto the manifold. We use an operation named retraction, which generalizes the concept W minus WL in Euclidean spaces for the stifled manifold. Sorry, I think this did not show up, so I'll leave. It might be a display error here. of
Hey Terry, you may use another version for the PDF. This maybe the wrong file.
I think maybe we can.
Or maybe we can escape this one.
Okay, yeah, I can just skip this page in that case, I think.
Yeah.
So. Yeah, I think, sorry. Okay, I think I'll just skip the following two. Okay, so once the model is trained, we need to do uncertainty quantification inference. The advantage of our model is that we have the closed form posterior expression it should be equation so actually equation 10, which is a Gaussian mixture model that has the potential to express complex distributions. So we have the analytical solution for the predicted mean and the variance for the new input here. And then quantile regression is more precise description of uncertainty, which we can get using the Monte Carlo method that simulates a batch of samples from the conditional distribution by the Monte Carlo method and then estimate the quantile with these samples. Here we propose a more accurate solution. The CDF can be evaluated with the given conditional mean and covariance. So for a given quantile, we can find an interval with linear search. Later, we have a comparison simulation for the two methods. So let's start with aleatoric uncertainty example where we design a data set with little noise in the data on the left side and high variance with data on the right side. In this toy example, both y and x are scalars, so we do not need the dimension reduction model for x. For simulated data, the fitted GMM is shown with means and covariances. With the means being the dots and the covariances being the ellipses. Let's compare Gaussian processes regression, also known as GPR, and our joint modeling, also known as JM approach. GPR regression gives a variance that does not depend on the input. That is, the predicted variance is of the same size for the entire region, while our approach models heterogeneous variance better, giving more accurate variance predictions. So returning to epistemic uncertainty example here, we designed a data set with less data in the middle region and sufficient data on both left and right sides. In this example, GPR gives a nice estimate of the epistemic uncertainty, and this is the reason why GPR is widely used for epistemic uncertainty prediction and Bayesian optimization problems. Our JM method also gives a favorable prediction. Finally, as future work, we will have a discussion on how to separate the two types of uncertainty if they exist at the same time. Our model is an implicit regression model, which uses a few hyperparameters, the choice of embedding dimensions P and a number of mixture components K. We look at the choice of parameters here through an example from the UCI dataset. Our evaluation criterion is the larger log likelihood. This is an example to evaluate the dimension of Z embedding. You can see that median of log likelihood is better with Z equals 5. Also here, we see the benefit of introducing dimensionality reduction. Our first data point is modeled directly with the joint model of Y and X without dimension reduction. Their log likelihood is significantly low. As shown in the plots, it is a bit difficult to decide the number of GMM components, as the number K is more dependent on the data set, particularly the complexity of inner structure of the data, which is understandable. This phenomenon also suggests that we may need some non-parametric models, such as the Dirichlet process mixture model, which can automatically select the number of mixture components. We'll leave this as possible future work. Recommended hyperparameters for K and Z is given here. Next, we look at the estimation of the aleatoric uncertainty on real data. We focus on the quantile estimation using the regression data set from UCI. To characterize the accuracy of the quantile regression, we apply two metrics: prediction interval coverage probability also known as PICP, the number of true observations falling within the estimated prediction interval and mean prediction interval with also known as MPIW, the average width of the prediction intervals. We are interested in calibrated prediction intervals that are narrow in terms of MPIW. We compared with 4 recent models for quantile regression: conditional Gaussian, dropout, quantile forest, and simultaneous quantile regression. Where simultaneous quantile regression has gained state-of-the-art results recently using a novel box to learn all the conditional quantiles of a given target variable. This is the evaluation 95% prediction intervals. Through the table, we can find that our model can be a smaller MPIW with high precision PICP. The linear search method always works better than Monte Carlo ones, which support the assumption that nearly closed-form solutions will be better than Monte Carlo estimation. We also did 85% prediction intervals estimation, and the result is similar to this one. We also get state-of-the-art results. So next we look at the epistemic uncertainty example in which we choose the active learning problem. The active learning problem is as follows. Train a model with an initial train set, evaluate the performance on the test set, estimate uncertainty for all data sets in the pool, and choose endpoints with the highest variance and add them to the training set. We compare with 4 well-known algorithms where the combined mean and variance estimator gains state-of-the-art results recently. So here we compare the performance of active learning on 8 UCI data sets. In the first 5 data sets above, our algorithm performs relatively well in terms of both log likelihood growth rate and final log likelihood value. We also have favorable performance on the other 3 data sets. We provide some potential direction for future research. One is nonlinear dimensionality reduction model instead of linear ones, which include like variational autoencoders and transformers. And then we can use a more advanced model instead of GMMs, such as dirichlet, process mixture, and energy-based models. Entropy estimation with potential application in Bayesian optimization, and we can separate aleatoric and epistemic uncertainty, sampling the low density area of the joint variable. So for separating aleatoric and epistemic uncertainty, where we have made some interesting discoveries and exploring whether they can be generalized into a practical method. In example, our data has both aleatoric and epistemic uncertainty. The middle region has epistemic uncertainty, while the right-hand side region has larger aleatoric uncertainty, as shown in here. In this case, the traditional model GPR and our JM model gives high variance for the 2 regions. So we can't distinguish it as aleatoric uncertainty of epistemic point. It will cause difficulty in active learning. However, it's interesting to look at the problem from the perspective of joint modeling X and Y together. And we showed the density of joint variable. It's obvious that the middle region has low density, which can clearly be separated from the region right hand side. And so single model approach for and then so this is the thank you guys for listening.
Okay. Right. Thanks, Terry. So, is there any question?
There's one from the internet, so yeah, they can actually ask it. They can talk in the class. You can talk on the internet. Go ahead, unmute and talk to us.
Hello, yeah.
Yes, we hear you.
Yes, ask your question.
Yeah, well, we welcome questions. Thank you.
Okay.
Joshua, we see your question. Can you talk via your microphone? Can I ask you a question? Just by
yes, go ahead. This is from Joshua. Okay. Benji's from this one. Someone else. Oh. Okay.
Yeah, thanks for the talk. I find it interesting that you model pretty much X and Y in one space. And I was wondering, this seems to work for regression tasks. How about very large scale tasks where you have millions of X images? I guess we would need to scale like to a lot of Gaussian densities, right? Is there any way you could get prevent a parameter explosion in that case?
Thank you very much. It's a very nice question. Currently, we just do the example on some UCI simple data set. The dimension of the data set is pretty low, but the number of data is okay. It's sound large. And for the further work, I think we can use some virtual autoencoder or some transformer based DN models to reduce the dimension of the input, like image or time series, and then try to build a joint model or to predict the uncertainty. I think the interesting thing is that when we put the embedding feature Y, embedded feature Z and the response Y together, so we can see something, some new ways to understand the uncertainty. Yeah.
Thank you.
Any other question? Okay, if not, then we are going to start on a first poster session, which will start from 11:30 to 12, 1 hour. And we have just one online post presentation, which is pre-recorded. So I'm going to put in the loop that if you want, you can sit and listen the presentation of that poster. The rest are in the poster room, hanging in the, I think, 5 cents. Okay.
I mean, she's
Unmute.
I think so. Yeah, let's stay.
Okay. Okay, this is. Okay. Yes. Okay.
Hello, my name is Stefan Bühler and welcome to our poster presentation about our paper Defensive Perception, Estimation and Monitoring of Neural Network Performance Under Deployment. In autonomous driving, it is crucial to know if an autonomous vehicle left the operational design domain and in general anticipate uncertainty of the perception system. In this paper, we propose to address this by encapsulating the model within an uncertainty estimation envelope that is based on the Monte Carlo dropout approach. This approach does not require modification of the deployed neural network and guarantees expected model performance. The defensive perception envelope has the capability to estimate the neural network's performance and is extended by novel methods to reduce computational effort. Here you can see the system flow overview. Since the perception stack is trained for only one source domain or specific source domains, the defensive perception envelope informs the system if an unknown domain was entered and as uncertainty rises. On the top here, you can see our metrics that we used to estimate that uncertainty. And as already mentioned, we use the Monte Carlo dropout approach, which means we have multiple forward passes with the same input data and the same model, but we insert a dropout layer, and that allows us to have the possibility to have different predictions for the same input data. We then try to measure the difference of these predictions with the pseudo cross entropy metric that is written down here. The advantages of this metric are it is independent from the number of forward passes, it depicts the entropy emerging from multiple forward passes, and it smooths the uncertainty for small deviations while upscaling larger ones. Our first experiment was with the MNIST dataset. The MNIST dataset, I'm sure you all know it, is the dataset with handwritten numbers where you have the model was trained on the standard dataset, so the numbers were not rotated, but for the test set, the numbers were rotated anticlockwise up to 90 degrees in 10-degree steps. Then the uncertainty was calculated with our new uncertainty metric using 20 forward passes, so 20 predictions per number, and with a dropout rate of 0.4. Also, the error was calculated to compare our uncertainty metric, and we also looked at the maximal number from the one-hot vector. If we now look into this graph, we can see that the maximal one-hot number nearly drops, while our uncertainty value increases down here, up to about 0.4. Yeah, if you want to do this experiment yourself, you can follow this QR code here and you will find a notebook where you can find the code for that. Now coming to an autonomous driving problem, we have switched over to a dataset that uses semantic segmentation on street images. And yeah, the first experiment we did was to train a model only on day images, so on the day domain, and then switch the model over to the night domain. So use the same model that was trained only on day images on night images. And then we want to see if we can use our approach to see the uncertainty within the model. In the first image, you can see the input images. You can see two input images. In the second image, you can see one model prediction. Of course, there are more predictions for the same image. That's how the Monte Carlo dropout works. And in the last image, you can see for every pixel calculated the metric up here. And yeah, the more red the pixel is, the higher the uncertainty is within that area. Below here, you can see a plot showing the correlation between the error and the uncertainty of each image. The error was of course calculated with the label, or corresponding label of the image, and the uncertainty calculated as explained. Here you can see the corresponding errors and the uncertainties for the day model trained on the day domain, on the day images and on the night images of the test set. Here you can see it again for the day images and compared to the dawn images of the test set. And on the right here, we did another experiment by training a model only on clear data, so dry streets, and then using that same model with rainy data and with snowy data. Yes, there is one problem this whole approach has, which you probably already noticed, and that is that it's the computational effort for it. We use multiple forward passes on one image, and yeah, that would probably not be possible to deploy in an autonomous driving system because of the limited resources. To avoid this problem, we used now sequential data to calculate our uncertainty. For that, we did different experiments at different frame rates to see how changes in images affect this approach. As you can see, there is more uncertainty here on the, or maybe to explain the plot first, the dotted line shows our baseline, so our norm. Hello, my name is Stefan Bühler and welcome to our poster presentation about our paper Defensive Perception, Estimation and Monitoring of Neural Network Performance under Deployment. In autonomous driving, it is crucial to know if an autonomous vehicle left the operational design domain and in general anticipate uncertainty of the perception system. In this paper, we propose to address this by encapsulating the model within an uncertainty estimation envelope that is based on the Monte Carlo dropout approach. This approach does not require modification of the deployed neural network and guarantees expected model performance. The defensive perception envelope has the capability to estimate the neural network's performance and is extended by novel methods to reduce computational effort. Here you can see the system flow overview. Since the perception stack is trained for only one source domain or specific source domains, the defensive perception envelope informs the system if an unknown domain was entered, and as uncertainty rises. On the top here, you can see our metrics that we used to estimate that uncertainty. And as already mentioned, we use the Monte Carlo dropout approach, which means we have multiple forward passes with the same input data and the same model, but we insert a dropout layer, which and that allows us to have the possibility to have different predictions for the same input data. We then try to measure the difference of these predictions with the pseudo-cross entropy metric that is written down here. The advantages of this metric are it is independent from the number of forward passes, it depicts the entropy emerging from multiple forward passes, and it smooths the uncertainty for small deviations while upscaling larger ones. Our first experiment was with the MNIST dataset. The MNIST dataset, I'm sure you all know it, is the dataset with handwritten numbers where you have to predict the number from the image. The model was trained on the standard dataset, so the numbers were not rotated, but for the test set, the numbers were rotated anticlockwise up to 90 degrees in 10-degree steps. Then the uncertainty was calculated with our new uncertainty metric using 20 forward passes, so 20 predictions per number, and with a dropout rate of 0.4. Also, the error was calculated to compare our uncertainty metric, and we also looked at the maximal number from the one-hot vector. If we now look into this graph, we can see that the maximal one-hot number nearly drops, while our uncertainty value increases down here, up to about 0.4. Yeah, if you want to do this experiment yourself, you can follow this QR code here and you will find a notebook where you can find the code for that. Now coming to an autonomous driving problem, we have switched over to a dataset that uses semantic segmentation on street images. And yeah, the first experiment we did was to train a model only on day images, so on the day domain, and then switch the model over to the night domain. So use the same model that was trained only on day images on night images. And then we want to see if we can use our approach to see the uncertainty within the model. In the first image, you can see the input images. You can see two input images. In the second image, you can see one model prediction. Of course, there are more predictions for the same image. That's how the Monte Carlo dropout works. And in the last image, you can see
I think we're just stuck here.
Up here. And yeah, the more red the pixel is, the higher the uncertainty is within that area. Below here, you can see a plot showing the correlation between the error and the uncertainty of each image. The error was of course calculated with the label, corresponding label of the image, and the uncertainty calculated as explained. Here you can see the corresponding errors and uncertainties for the day model trained on the day domain, on the day images and on the night images of the test set. Here you can see it again for the day images and compared to the dawn images of the test set. And on the right here, we used another, we did another experiment.
So, for example, this is on the color and I remove the green color. Okay. Yeah. So this one, I am saying, what is basically one plan in semantic sense. For example, this one is related to
abbiamo portato queste robe qua. Abbiamo messo
one of the symbols in this is we have data. This is then about the variation of so there you can find source we can really corresponding to the current issue. And then we need to connect this one with the application. So we actually very application models. If it's wise, first use traditional encoder so that the form or reconstruction. Then you can reconstruction. So they are trained. They are trained separate. But so we want to combine them together. We want to explain. So you can see this forward propagation actually combines this. So that's
somewhere straight. So
no, I think we are only here. Yeah. I understand. I still about it. They get to do a lot of.
Depends on the
this is basically we also find out if there's a current. To me, we can treat all the together correctly.
Sorry guys, can I ask you to move your stuff from the last two files? We're gonna make more space for the other folks. Anybody sitting in this? Yeah, it's this question. Oh yeah, no.
That's right. On the.
Or others.
Yes. No problem.
Actually, maybe it's super fun.
Yeah.
Maybe more, so don't remove things that line. Make sense?
Oh, yeah.
So that's what you can leave, but this story you put behind.
Yeah.
It's here. Watch out, this is just a.
And are you assuming? Hopefully this will help.
Yeah, yeah.
That's ours.
Yeah.
You're good.
You're local, right?
So-
So you're local.
Now in 20 minutes.
You can have.
Actually, that requires some. Oh, okay, then. Yeah, that's.
They were not.
I counted in the five because we were setting up like.
Yeah, that's what I'm wondering, because space issues with this, like, I don't want to take those. No, we're setting that up for you. You have a poster, even though you have I mean, I should have it with me.
I think he was counting, I don't know which list he was using, I counted 8.
There should be space for.
They don't modify. Bello, bello. Anche vedete, lo sai che io sono
I'm sorry, the UK based like
People listen to that.
Yeah. Unless you want something like that.
Yeah.
And if you ask everybody. Another week, there's like some, so what's the equation of y?
Oh, yeah, but you just saying, so hopefully, very already showing. And then also as soon as we are not using this one as
One week in Hawaii and then 1 week here. Obviously, like here. Really?
Wenn wir nicht wissen, ob wir 1000 Klassen haben oder 3 Klassen, dann aber du kannst solche Methoden damit auch testen.
Da benutzt dann halt immer diese eine Layer exakt, um beide Embeddings abzuleiten, weil hättest du ja die andere vorher anders ausgegeben.
Also die einige die haben die quasi License haben halt das CSN-Layer und dann kommen die ganzen Layer. Ja, eigentlich wieder einzugreifen. Wie das Ganze noch zusammen.
Yeah, a lot more here and then text me. You're good to share.
Also ich meine,
You can actually hear you right now.
Yes.
Talk to you.
Okay, shall we start?
The next session.
Next session?
Yes, the next session is about. No, we have a 12:30 to 1 o'clock in here. If you want to eat lunch.
Oh, okay.
Yeah, yes. So, yeah. This is the next half-hour session. That's all.
Is there scheduled lunch?
So he can start talking whenever he wants.
Don't take away lunch.
Right.
Oh,
Okay, I would like to announce that yes, our next speaker is Professor Marco Zantolo from SIA Institute. He will talk about casual inference meets epistemic AI, practical general methods for counterfactual and information fusions.
Okay, thank you very much. I hope you can hear me and see my screen in particular. Is it okay?
Yes, we see. Just one
okay.
Couple of minutes, people are coming to see. Just 2 more minutes, please. Everyone. Okay, Michael, the floor is yours.
Okay, thank you very much. So again, thank you to the organizers for inviting me. This presentation is based on work that I've been doing with the people that you see here, and I guess that a couple of them are there as well, as I seem to see. So we are all from ITZA, apart from Rafael Cabanas, that now is in Spain at the University of Almeria, formerly was a postdoc at ITZA. This work is work that has been scattered around a number of conferences, as you can see below in the slide, and recently a couple of papers submitted to journals. Okay, so let's start with an example. The example is the following. So suppose that, here we are, suppose that you have a headache and you take an Aspirin and your headache goes away. We would like to represent this as a causal problem, so we use X and Y and represent the causal effect of X on Y with an arrow. And then we would like to understand in particular what is the probability that our headache has actually vanished thanks to the aspirin. This is not as maybe trivial as it may seem. We might have a data that tells us, something that goes to that direction, as you can see, with the conditional probabilities. But at the same time, these are population data from which we estimate probabilities, and they are not really talking about me, or about you that have taken the aspirin. So I would like to know what is actually my probability for which, the aspirin has had an effect. And in this case, I would like to know, for instance, something like this. What if I had not taken the aspirin, if my headache in that case would have stayed? So this is a question really about me that maybe I would like to answer with observational data and therefore population probabilities. In causal parlance, then we would use this thing which is called PN, probability of necessity, this expression that you see here. And probability of necessity, embeds this strange notation, which is a counterfactual notation, y sub x equal to 0, which means indeed a counterfactual. So in case I did not take the aspirin, so x equal to 0, what would be the probability that I would have headache, so y epsilon to 0, given that in the real world I took the aspirin, x equal to 1, and the headache vanished, y equal to 1. So this is a counterfactual thing. It's a quite strange item if you want, but the cool thing is that as strange as it seems, we can answer these type of questions in a probabilistic term once we have a fully specified structural causal model. So a fully specified structural causal model is similar to the graph that you saw before, but in addition, we have two additional variables, u and v, and these are called exogenous variables, that are the variables that connect the basic model to the external world, external reality. Usually, we should have also probabilities on top of the exogenous variables, and in particular, we should also have deterministic equations in the internal nodes, which are called structural equations. So these are deterministic equations that determine the values of, in turn, x and y, depending on the parents. Fully deterministic, so there is no uncertainty here. The uncertainty is only on top, on u and v. If we have a fully specified structural causal model, we can build a twin network. A twin network is very simply the same graph that you saw before duplicated, even though the two parts are connected via the exogenous variables u and v. And the idea here is to represent both worlds at the same time, jointly. So we have the world below here, where we took the aspirin and the headache vanished, and the alternative world here above that did not really occur, where we don't take the aspirin and the headache maybe stays. Okay. So we create the joint network, the twin network to talk about the two worlds at the same time. In the other world, so in the hypothetical world, we should not take the aspirin, so we implement this by a do operator, like in pairs notation. Therefore, we remove the incoming nodes into the x prime variable and set x prime equal to 0. And then we compute a query, and the query in the twin network is a very normal query, so a probabilistic query. There are no counterfactuals, because the counterfactual, as it was expressed before, now becomes a normal probabilistic query in the twin network, where the node we want to query about is y prime. So it is possible to reply to counterfactuals if you have fully specified structural causal models, but of course we need a number of things, because in many cases we don't have the probabilities on top of u and v, and also we might not have the structural equations for the internal nodes. So what do we do? Say that we are in this situation, so we know nothing apart from the joint distribution of x and y that we infer from data. We don't even know the cardinality of u and v, but even so we don't know the cardinality of u and v, what we can do is to still determine their cardinalities if the variables in the structural causal models are categorical. In this case, they are Boolean. And the reason is the following. So consider y, for instance. There are a finite number of functions that may map x into y, because x has two values, y has two values, so there are only 4 possible functions that transform x into y, and the 4 functions are these guys here. So y can be constant on 0, constant on 1, equal to x, or equal to y minus x. There are no more functions. So if you consider that there are only 4 functions, what we can do is we give 4 values to v, and we, in a sense, enable v to list enumerate all these possible 4 functions from x to y. If there were more values for v, like 5, this would mean that we should have to duplicate sometimes the function from x to y. So the same function should be repeated twice, but we don't need it. So we can just clump these 2 values that refer to the same function and go back to the state of 4 values for v. So we determine the values for v based on the number of possible functions that implement the transformation between x and y, and similarly for the function that is related to x. Then once we really want to implement these things in practice, we may as well implement the functions by 0-1 value probabilities. So we use a very big table like POY given x and v, like in a Bayesian network, and we represent the functions with 0-1 probabilities. So this first block here for v equal to 0 is the effect that the y is constant on 0. The last one means that the y is constant on 1. This is y equal to x, and this is y equal to 1 minus x. So we can implement the deterministic functions eventually through 0-1 value probabilities. So once we have this, we have essentially the structural equations, we have the cardinalities for the exogenous variables. We are only missing the probability of u and the probability of v, because they are usually latent variables, and we only have information about x and y in the form of a distribution. But then what we can do is to backpropagate this distribution, the joint of x and y, back onto the probability of u and the probability of v. And if you do the calculations, you get something like this. And in particular, you see that the probability of v is not really a single mass function, but it is a set of mass functions that depend on the parameter t. This means that there are multiple unconditional probabilities for v that through this structural causal model produce the very same empirical joint probability for x and y, the very same data. Okay, which is something very well known in causality, which means that the problem at hand is non-identifiable. Multiple probabilities for the exogenous variables can create the same joint on x and v, or x and y, sorry. Okay, but then still we have a probability for v, even though it is imprecise, and therefore we can still create a twin network out of our partially specified structural causal model as before, and this is before it was a Bayesian network. Now, since v as a Credal set, a set of distributions instead of a single mass function, this becomes what is called a Credal network. So essentially a Bayesian network extended to deal with imprecision. And we can use algorithms for Credal networks to solve the query that we were after. And we obtain an exact result, which is the probability of necessity between 4/9 and 5/9. So you see, by doing all this construction, we are just using essentially a very simple graph and the data for x and y, and we need nothing else because all the rest essentially has undergone very, let's say, very soft assumptions, like, canonical specification is almost least committal. The cardinalities are least committal. So we are really doing something in a very least committal sense, and still we get an answer that is related to an individual from data about the population. So we can infer probabilities for a specific individual in a counterfactual sense from population data, which is quite cool. In principle, these technologies, this methodology can solve all counterfactuals. You can take any complicated graph and structure and so on, but of course there are problems at some point, and the problems are the following. So for Markovian structural models like this, where we have one-to-one relationship between exogenous and endogenous variables, the system that the procedure that I showed to you works. With quasi-Markovian ones, where there are one-to-many relationships between the exogenous and endogenous nodes, like here, it works, but it increases the complexity. And with fully general structural causal models, like in this case, where we can have a double arrow pointing from different u variables into a single x variable. So for non-quasi-Markovian SCMs, this becomes quite complicated also because in general we have a theorem, that tells that causal inference is NP-hard even in polytrees. So as opposed to Bayesian networks, where in polytrees we have polynomial computation or linear size computation, in this case we have NP-hardness also in polytrees. And this means that we need to approximate at some point. We cannot just use exact algorithms for computing our queries. One idea to do this is the following. So, recall that exogenous variables very often in causal problems are latent, and this means that they are, missing with probability 1. And this is another way of saying that they are MAR, missing at random. Since they are MAR, we can use the EM, expectation maximization, to quantify the uncertainty about the exogenous variables. So we do just a very bare, plain EM, and we set we have data for X and Y. We have a data set for X and Y. We have a random initialization for POV and POV, and I run the EM up to convergence, and then we get some updated POV and POV. And this is a traditional EM, but we have a result that tests that at convergence, in this case, PU and PV belong to their corresponding critical sets. So, there are exact critical sets that we may not be able to access because the problem is complicated, is NP-hard. We don't know these critical sets, but we know that through this procedure, through the EM, we are able to sample inside the critical sets, so to approximate the shape of the critical set. And therefore, it's not difficult that we can approximate the solution of the problem in this way. So every time we sample a fully specified structural causal model, which is compatible with a partially specified one, where we don't have all the information, we compute the counterfactual for this guy, because this guy is fully specified, so we can compute the counterfactual precisely, and then repeat. Repeating means sampling again another one, computing the counterfactual, and so on. So the procedure is more or less like this. Eventually, we get a number of points that lie inside the exact interval, which in this case is 4/9, 5/9. So we will sample points inside this interval and approximate it from inside. So this is the approximation that we are proposing with an algorithm that we call the EMTC. In practice, what we get is that already in 20 runs of the EM, we have shown that we can get a reasonably good approximation to the exact interval. And it works in general. So it works for any structural causal model, partially specified. You can compute any counterfactual. The main constraint that we have is that the variables need to be categorical. Okay, so why does it work? It works for this reason, because we can show that the likelihood is something like this. So just a sketchy idea of the likelihood. The likelihood is kind of a unimodal function where there is on top of it a plateau of global optimum points. So there are not local optima in this likelihood function. There are only global optima, and they are all concentrated in this plateau on top of the function. And we have a theorem that tells that the points corresponding to this global optima are if and only if the fact the corresponding unconditional mass functions for the exogenous variables are in their respective critical sets. So essentially, this is justifying the fact that by running the EM multiple times, we are sampling the unknown critical sets. And okay, empirically, it seems to work well. This is the root mean squared error according to different networks, which, as you see, is quite good already in 20 iterations of the EM. And then we have a theorem for guaranteeing, again, the quality of this approximation in the following sense. So, we produce this approximate interval AB, which we know to be inside the exact one that we don't know, A star B star. And we would like to know how far is AB from A star B star. So how bad is the approximation, or how good is the approximation? And we have a probabilistic guarantee given by this theorem above here. So we essentially establish a certain distance from the true interval A star B star, and we have a probability by which our approximation is away from that distance, from the actual interval by that instance. So we have probabilities that tell you how good is our interval. In particular, if there is a particular case, okay, we have always the same result from the NCC, so the problem, produces always the same counterfactuals, even if we run it over and over. It's enough to have essentially 9 runs with the same value of the counterfactual, the precise value of the counterfactual, to be sure at 99% that the problem is identifiable. So there is not an interval, but a point as a result of the algorithm. We have done an application to a palliative care example. So this is actually a true problem. So you see a graph here, a causal graph drawn by an expert in palliative care, where the goal is to understand whether a certain terminally ill patient is dying at home or in the hospital, where of course the goal will be to have the patient die at home. In order to reach this goal, we can act on 3 variables, which are the light gray nodes. So make the patient aware of death, making the family aware of death, and eventually also asking triangle, which is an association of volunteers, to assist the patient at home. Okay, so we want to understand what is the best node on which to act, so in a causal sense, so what is the best intervention. And we have observational data, just about 116 patients for all the variables in the network. There are no local confounders, so we can take the model to be Markovian, so one-to-one correspondence between the U and the X variables, and then use the canonical specification as I showed before. So we don't need to know the structural equation, we just list all the possible structural equations. So again, in this case, we need just the graph and observational data. All the rest we can build up from scratch in a sense. And what we want to compute is this counterfactual, which is called probability of necessity and sufficiency, which means the following. So say that X is a triangle. We want to compute the probability that if I enable triangle to make home assistance, the patient will die at home, and at the same time that if I disable triangle to do home assistance, the patient will die in the hospital, which is a way to say, what are the patients that truly benefit from the treatment, because depending on the way in which I set the treatment, I will have what I want and what I don't want. And I do that for all the three variables in the graph that I can control. What we get is the following. So there we have intervals, as you see, or probability for the PNS, computed by the MCC, but still, in spite of having intervals, you can see that triangle strongly dominates the other two variables, because the lower probability, 27%, is far bigger than 11%, which is the upper probability of the two other guys. So this means that we should act on triangle first, and then we know already that we can change the fate of 30% of the patients by acting on triangle. And this only using observational data and just drawing a graph, so everything is very simple. We don't need to do experiments. Also because, when there are counterfactuals, you cannot really do experiments, because on the same person, you have to enable and disable a certain controllable factor, which you cannot do by an experiment. Okay, the work so far has been summarized and described in quite some detail in a recent paper that we have submitted to a journal. So if you want to take a look, you just go to the archive and the paper is there. Okay, then what we have done, we have extended the MCC to handle selection bias. Selection bias is this thing. So the fact that the sample that we use to learn the graphical model might not be a random sample. So it might be a sample from a specific biased subpopulation. And this is very, very frequent in application. So for instance, in this case, we're assuming that the treated males and untreated females are systematically not reported. So we don't see these cases, and all the others we see. This is a case of selection bias. We have the selection bias, but of course, we would like still to make inference about the overall population, not just on these guys. So we see this subpopulation, not just a random sample, but a systematic, non-random sample of the population, and still we would like to know something about the overall population. We do that by adding a selection node, like the S that you see there, that represents the selection function. So in this case, the fact that those guys are not reported. So it's a logical function that lights up when the guys are not reported. Can we still say something about the overall population? We can, because we can show that essentially we represent the data set in the following way. So the original data set is split in two: the one of people that are represented, selected in the sample for which we have information, and the zero of the guys for which we don't have information, and therefore, as you see here, we have all missing values for 226 samples, for the treated males and untreated females. We have to modify, of course, the iteration of the EM in this case, because we have, in this case, not only to fill the missing values here in D1 as before, but also the missing values of all the variables in D0, which is something new. In spite of this, the theorems that we saw before still hold, so the log likelihood is still unimodal, and again, the global optimum points are corresponding to sampling the unknown critical sets. So we can still approximate the unknown critical sets, so we can still run the experiments, and get, as you see, again, nice results compared to what we had before. If we apply the same idea to the palliative care as the same example as before, so these are the results that we saw before, but now we assume that we have a selection bias. So we assume that the data that we have are data only about very, in people in very bad conditions. Either the symptoms are very bad, or the Karnofsky ESI. Karnofsky is an index that tracks the progression of the disease. So we are assuming that we only see people in very bad conditions, but we would like to know, to make inference about every possible patient. If we do that, we get the intervals that you see here under bias. So the intervals get wider, of course, because in this case, we are lacking information compared to before. We are lacking information about a substantial portion of the population. The intervals get wider, but as you see, the triangle still dominates. So even if we have selection bias, we know that we should act on triangle to have the result that we want, and that at least 22% of the population would benefit from this treatment. Okay, last extension that we have done is extension of the MCC for fusing multiple data sources, and the idea is the following. So it's a classical data fusion problem in the causal flavor. So imagine also if you are in a medical case, you will have multiple labs in different cities that maybe address the same disease, but they will have different procedures. Some labs will do experimental designs, so randomized control studies. Some other labs will collect maybe observational data. Different labs will have different proportions, for instance, of males and females. And at the same time, you would like to take all these things together in a coherent setting and compute counterfactuals maybe in another lab where you don't have so much data, or you have different types of data. What do you do in this case? So in this case, you see a data set where we have interventions, giving the drug, not giving the drug, and then observational data, so not just interventions, but people that just take on or not take the drug according to their will. Say that the graph underlying this problem is the following. So there is a confounder between gender and survival, and there is another exogenous variables on top of treatment, VUT2. So what we do in this case is the following. First of all, we append all the datasets one after the other and create a single dataset where we have added, on the other end, a variable W that lists the type of treatment that we are going to do, whether it is giving the drug, not giving the drug in a controlled fashion. And W empty instead is a symbol to represent observational data. So the fact that we are just observing, not making interventions. So in this way, we can just glue together all the data sets collected through all these possible labs, data sources. And then we modify the graph as follows. So we add variable W on top of all the endogenous variables. And the idea is the following, that once we know, for instance, that variable W is stated W empty, which means that the data are observational, we put on V2 the structural equation corresponding to observational data. So, the ones that you are giving at the beginning. If we instead W is equal to drug, this means that we are doing an randomized experiment, randomized controlled experiment. In this case, we insert in V2 the structural equation that tells that the V2 does not depend on U2, but is fixed directly to the value of drug, and so on and so forth. So essentially, W gives us the possibility to do implicitly the surgery that we need to do every time in the graphical model describing the disease. So if we do this transformation, eventually the graph that we have is a graph, an SEM as before, and we don't see anymore the problem of having to fuse information. So we have a single dataset and a single graph, and then we can run the previous algorithms as we were doing before. So we take everything back to the standard usage of the MCC, and therefore we can fuse multiple data sources. Okay, again, this has been described in a further paper that you can find in the archive. And finally, very briefly, this is something that David, that should be there, has already presented at another workshop today at UAI. So I'm very brief here. You can ask maybe questions to David afterwards. The idea is that we can speed up the computation on structural causal models if we compile the structural causal model into a probabilistic circuit. Because the structural causal model is essentially a Bayesian network, or a partially specified Bayesian network, if you want, loosely speaking, let's say. And it is a special Bayesian network in which the structure is fixed, and we have to perform very many queries, but on a structure that is fixed and equations that remains constant. So you can compile it once and execute it very many times. If we do that, what we get is roughly 1 order of magnitude faster in the calculation. So it's much better to first compile it into a circuit, because a circuit can take advantage of zero probabilities, and there are lots of zero probabilities in structural causal models, and of course also asymmetric independencies. This work is joint work with Adnan Darwish, as that you see here, and the student is Zuo Chen. Okay, just to conclude, my point is that there is a natural link between causal inference and epistemic AI. These models are robust, are made of multiple distributions. So there is a very direct and natural connection to, in particular, Critter networks and imprecise probabilities. We can use even the algorithms on Critter networks to solve very general instances of structural causal models. Problems are hard, of course, as we saw, and therefore we need to approximate it. The MCC, on the other hand, is quite simple, so I think you can apply it in your problems very quickly, especially because the software is free. Davide has been creating the software for the most part, and this is relatively easy to install and use. It gives inner approximations, the MCC. We give it guarantees on the outer ones through credible intervals, and everything can be made parallel very quickly. Of course, we have been working on this for 3 years, but there is still a lot of work to do. So if you want to join, you're very welcome to join the effort. And thanks for your attention.
Any question?
Thank you so much. It was very interesting. I was having one question. Let's assume you have the Credo set of your networks is just all of the networks, all of the SCMs that will fulfill your joint distribution. And then you run a counterfactual query. Would that output you the same thing as if you would just run the query, like the conditional likelihood on the original network? Because I'm not seeing where you're inserting new information that would change the output.
I don't know if I understand your question exactly, but okay, if you agree with me that at some point we have to use a structural causal model with structural equations inside, any method that works with that will produce the same result, in the sense that you will produce something that must be unidentifiable, compatible with the empirical distribution, so the distribution on the endogenous nodes, and that spans all the possible probabilities for the exogenous nodes that are compatible with that. If you say that in the conditional likelihood approach that you would like to use satisfies these requirements, I think it will be producing exactly the same results. But notice that in order to calculate counterfactuals, you definitely need to have the structural equations, because otherwise you will be staying on the second layer of Peirce hierarchy. Without structural equations, you couldn't compute counterfactors in general.
Okay, maybe as a follow-up. Let's say I want to have a counterfactual query, but I have no knowledge about the causal process. So could I then just say I evaluate the counterfactual query in every possible SCM that will fit to this distribution, and that would be like my actual result?
Yes, but I agree. But in every possible SCM needs to have structural equations inside, right? We agree on this, correct?
Yeah, okay, yeah.
Because if it does, then I agree with you completely. But it needs to have structural equations inside.
All right, thank you.
Yeah.
Hey, Marco, Fabio here.
Hello.
Long distance call. I wonder if you're familiar with causal representation learning. Can your method be used for causal representation learning? So learning representations that contain information about the causal structure of the world. This is also related to hallucination, for instance, in large language models, which suffer from inability to really understand causal structure of the world. So yeah, my question is, can your work be extended to causal representation learning?
I don't know if I'm familiar enough to give you an informal reply, but this is an algorithm that solves essentially causal problems in their full generality apart from the restriction to categorical variables. But of course, you need to have a causal graph, at least. So the very requirement that we are needing is having a causal graph, causal graph and data about the endogenous variables. If you have that, we can do everything. If you need to learn the causal graph, that is another story, of course, and there are lots of approaches to do that. Without the causal graph, yeah, we wouldn't do anything because we definitely need that. It's an input for us.
Okay, maybe we can have a conversation on the side to do that.
Yeah, but Fabio, what maybe you may be interested in is that, especially in some cases, the critical set that you get is a belief function.
Mm-hmm.
Actually, in many cases, because you know, in Markovian SCMs, you definitely have a belief function, so it joins some of your, I guess, you know, experiences in
yeah.
precise
What I'm really interested in the causality domain right now is the link between causality and understanding, because you know one of the criticisms of the largest models now in existence is that they don't really understand the working of the world, and causality, the causal structure of the world is a big element of that. So I'm starting in the direction, you know, that and also what is the role of uncertainty in understanding the causal structure of the world?
Well, I think, you know, in large language models, we have just a very big deep neural network, so then it has no notion of causality there inside, right? So if you see what Peirce says, for instance, in this case, is that you should use a causal model, like maybe the one that I've been showing, and then you should estimate structural equations with deep learning, because then you can, you know, fit very complicated functions. So like using a deep neural networks for estimation, and the structure, the SCMs for, you know, the high level structure that drives the reasoning and these things. How to keep the two things together is not trivial. I think it's not easy to do. And there is already quite some work already by Elias Barenboim and also Benjo that together made a paper like a couple of years ago about joining deep neural networks and SCMs.
Any other question? Marco, I have one question, please. I'm wondering if maybe if we go to simpler models rather than Creedal sets, this can reduce the complexity, like we go for probability intervals rather than Creedal sets.
Well, you know, in a sense, if you want to, we are kind of using probability intervals, but the truth is that we have big and complicated Creedal sets inside. So you can always approximate that by probability intervals, but the question is how much you are losing. And we are providing inner approximations. Maybe if you can try to outer approximate the Creedal set by probability intervals, so you would have outer approximations. I'm not sure exactly how to do that, but the risk is always that you get very, very, you know, weak answers. So, but I mean, it's definitely something to try, because the question as usual is that we are quite good at providing inner approximation and not so good at providing outer approximations that make sense, that are strong. There is some nice work by Spitzer and colleagues. You know, Spitzer was a former PhD student of Peirce in the US that made a very big and complicated optimization problem that also gives outer bounds. But they don't really publish the, you know, how effective is that in practice, how fast is it, and so on. So they don't have an extensive empirical study, so it's unclear to know how it works. And from my experience, you know, in Creedal networks, dealing with a problem, you know, face to face like this with an optimization problem doesn't work so well, especially for mid-sized problem already faced now, because it is too complicated.
Right. Thank you. Okay, more questions? Okay, then I would like, again, thanks to all speakers for the first session and the second session after the poster. And I invite all of you which are present here for lunch break starting from 1 o'clock to 2. And please come back here at 2 o'clock. Thank you.
Thank you.
Hey, why not?
Can I borrow your ID to get into the
It's all good. It's the same place.
That was not used, all in one month. So,
I got a GPU.
yeah, we do have other GPUs. There were a lot of GPUs in the but we have hundreds and
You're welcome.
I developed like a nice limits and biases schedule. I could just basically overthrow that. Like, I just start agents on the GPUs and they waste for dry. Yeah, thank you. So it's very scalable to do that. I would just recommend you use the biases and tweaks in there.
Okay.
That has to look like defining your own shells.
Did you automatically sort of run all the data sets?
Yeah, that was all of it.
I don't really run that many.
Lucky you.
But yeah, it was fun. You also want to go for lunch?
Yeah.
That sounds good. I really like that last talk because it makes kind of sense to me to have. Because if you have non-identifiability anyways over like SPI, the last talk.
Yeah.
Ran out. Good. Yeah. Might want to go visit you.
Whoa,
Yeah.
there's scary, large.
Most of them is salads, but there's no harm. I think they open up everything. So this one's making sure people. Yeah. Find out what it is. And there's nothing left as usual. Oh, well. Oh, well, let's find out what this is.
This one. About you?
I'm just. I wish I stood. I did. I don't
Oh, okay. What's happening?
I guess. I don't know. Do they really? But it ended up, I ended up having more.
I mean, I don't think like even if you play one that sounds like you're done forever. Please learn. I've tried to learn algebraic geometry at least 4 times very focused results. There is a 5th time going on right now, and it's going somewhat better. So
Sorry, it was what I was seeing me out of.
seriously,
Yeah. It is. I wish I could. It's not making. Yeah, that was.
Do you know, I heard that we needed like a fund drive to present. Do you know if that's true? If it's
No, are you listening?
Yeah. Sorry.
No, it is. I was where on
I saw that by. I just haven't gotten it onto this because.
And did they use your own?
I didn't get.
Wait, this is-
The issue is I need to get it on here from them.
Okay, just something like this.
Okay. Maybe then, yeah.
No. That's all. Credentials.
Do you want me to help? Do you want help with the volunteer?
Yes, Alan, not Alan, but Adam. Adam's up to help me too, so yes,
Right.
yes. So Adam, this is another helper here. Yes.
Should I get the wonderful? That's fine.
My side.
I'll just like.
I can just play a link on here. If I can put an orange to type it, but
Not yet.
No.
Not yet. It might be
Is
soon.
this on the schedule or the?
Oh, wait, I thought you can.
okay.
So you have to share it. We have to stop and share. You want to put it up on the screen, right? You want it to be seen on Zoom. There we go. And you have to share it. Are you the first speaker, sir?
I'm the second. I
Second. Oh, okay, by all means, by all means. Yvonne should be back. If I'm pronouncing it. There he goes. The second speaker is putting his presentation on your computer. And that's Adam the help or helping him out.
Yeah.
Why this is out? Please. Did you copy your file or what you were doing here?
I just want to find the meeting link.
Here?
Yeah.
Oh. Okay. You're here. It's not the correct one. This is not the correct one.
We should be already connected through Zoom. We're connected to Zoom.
This
Unless you need, unless I need.
here. This one. Correct, Zoom.
So who's the first speaker?
Yeah, I was.
I have his name.
I prepared here, but they're all gone. I don't know why.
I have his name, but are they here? Or her name?
Here.
Recording in progress.
Yes, it's always they just being one. Right. Yeah, it was okay. So yeah.
Yes.
Yeah, this one's, no, but you gotta stop here.
I
know, yeah.
Oh, yes.
Before. So hopefully our second speaker shows up with the presentation. Yeah. Our first, you already have this. He's the next one, the gentleman behind the second.
Okay.
That's
Who's the first?
the first person is not here. So we get here. Yeah, 5 minutes, right? Plenty of time.
So is obviate super. Or Carlton Gold.
I'll look on.
Did you move next speaker?
No. Not online, so. Should be here. Do we go in reverse order? If that's the case.
Maybe we can switch if he's not here.
Okay. All right. Sir, when you're ready, if he doesn't come, we'll present you first. Okay.
You have a presentation already?
I'm sorry.
You have your presentation?
Yes.
Did you send?
It's on a.
Oh, okay. We can continue. You say this, go just. Which is not installed.
Okay. Then I have this PDF also.
Let me see.
I'm gonna go ahead and stop your share so you can bring it up.
Okay, I go to the video. Where is it?
Schön, ich will auch nicht mit der Plastikgabel mein Essen essen.
Ja, so wie Gott das.
Ja, genau. Oh.
Is it? Yes, we are.
No, yes, yeah.
Not like four.
No, yes, yes, yes. No, but
Okay, our next speaker is Anna, which he will talk about model development and active learning with missing non-analytical components. So we skip the first one and replace with this, and then we will see if the first speaker is here or not. So, hello. Yes, you have.
Thank you. Hi, everyone. I'm Alan Mishler. This is some work with colleagues at JP Morgan. So the fundamental challenge that we set out to address is the fact that when data is missing not at random, it generally induces bias in predictive models that are trained using that data. And of course, missingness not at random renders many parameters of interest non-identifiable, but we're specifically concerned about the impact on performance of predictive models. So we consider several classes of solutions to try to address this. The first two are about making the best use of the data we already have, which contains missingness not at random. This is something of practical interest in a business setting because this kind of missingness occurs frequently, and yet you may still need to arrive at a usable model. So the two classes of solutions in this category we consider distribution robust optimization and Bayesian regularization. And then the third type of solution we consider is active learning, specifically tailored to the missing not at random setting. And this is applicable in case you have the opportunity to acquire new data of some kind. So suppose we have features X, a prediction target Y, and a missingness or observability indicator D. So that instead of observing Y, we observe the product dy, meaning sometimes we observe Y and sometimes we don't observe Y, and when it's missing, we arbitrarily replace that with a 0. So the literature generally distinguishes three types of missingness. One where the missingness D is completely independent of everything else, one where it's independent of the outcome conditional on the observed features, and one where neither of these situations obtains the missing not at random setting. So these are some possible causal graphs, not the only ones that could give rise to these patterns of missingness, just to supply intuition. And the missing not at random setting, if we think of D as a treatment rather than a missingness indicator, we can see that it's structurally equivalent to the presence of unobserved confounding in a causal sense. So suppose our target is M of X, the regression of Y on X. In case we want to minimize mean squared error for regression or minimize classification error. We're going to split this into two regressions, the one conditional on D equals 1, so the one that is observable, the one that we can estimate from the data, and the one conditional on D equals 0, which is not observable from the data. That's the regression for the missing data. And then the observability propensity, the probability that we observe Y, probability that D equals 1, conditional on a particular value of the features X. So if we just expand this very simply by the law of total expectation, we get these components that we can estimate from the data, the missingness propensity and the M1 of X. And then we have this component M0 of X that we by definition can't estimate from the data. So this is the target of our three different solutions here. So the first one, distributionally robust optimization, starts with an uncertainty set of distributions. These are distributions that in some sense we consider plausible as representing the data generating process. Equivalently, I guess you could call this a creedal set. It's just another set of distributions. And then the conventional target in this setting is the minimax optimal predictor F star. So among some class of models or your hypothesis space, whatever you want to call it, script F, this is the model that minimizes the worst case expected loss over that uncertainty set. So traditionally, DRO generally is construed as dealing with error due to finite sampling. So it's common to construct uncertainty sets by reference to the empirical distribution, for example, as a Wasserstein ball in distribution space around the empirical distribution, or with some kind of moment constraints relative to the empirical distribution. things like that. But we are interested instead in constructing P to explicitly capture uncertainty due to missing is not at random. And the initial motivation was thinking about a lot of domain settings where this type of missingness occurs. There are experts who have some kind of intuition, maybe not easy to quantify, but they have some kind of intuition about patterns of missingness, and we were thinking about what kind of frameworks can we provide such that they can inject their expertise into the modeling process. So we have the true unknown observable distribution P. Again, note this is over dy and not y itself. And then we define the bias function, which is the difference at any given value x between the observable regression, the one we can estimate from the data, and the one we actually want to know the regression of y and x. This is commonly used for sensitivity analysis, for example, in causal inference. And then at each set x, we suppose we can specify some c of x, which is a set in which the true bias function is assumed to lie. And typically this would just be an interval, but it doesn't have to be. I'm leaving out a few details for simplicity, but basically we assemble all these pieces together into an uncertainty set that consists of all distributions that are equivalent to the true observable distribution and whose bias function, so this Q is over xd and y now, but the Q of xd dy is equal to the observable P, and whose bias functions are supposed to lie in these sets that we've somehow specified. And again, we can understand this as containing all distributions that we believe could plausibly have given rise to the data. So we can think of these C of X, these sets as equivalently as either domain knowledge, you specify a particular C of X, or sensitivity parameters where you vary them. Let's say you specify intervals, you vary their width to see what the effect is on downstream models.
Can I ask one question? Sorry.
Oh, sure.
Do you need C of X? Can you derive nothing if you don't use a C of X?
You land at the, if C of X is infinite, then I think the solution is undefined. I mean, I think that you do, otherwise you either land at an undefined solution or the trivial solution, which is just the regression in the observable data.
I suppose my question is, can you derive something, meaningful without making strong assumptions about each other's bias?
Well, let me see if this answers your question. I think the answer is kind of, at least in terms of what we've been able to derive so far. So if we, yeah, so one answer is whatever the C of X's are, we get a closed form solution, which is nice. And the solution is precisely the observable regression plus an offset that's just the midpoint of the range of possible values of these C of X's. So if the C of X's are symmetric, then we end up just back at the observed regression. So we get something, but we get something sort of trivial. So yeah, it's nice that it's a closed form solution. It's easy to estimate, but not super informative in practice. We have another proposition I'm not showing here, which is if we don't use these bias functions, but we just impose bounds on y, or suppose that y lies almost surely in bounds that might be conditional on x, and we get a slightly less intuitive solution, but still a closed form solution that we can estimate. So that might also address your question, because we don't actually formulate the bias function there, but the bounds, we formulate bounds on y itself. So yeah, these solutions end up being kind of too conservative to use in practice without sort of very rich domain information. So an alternative that we consider is a Bayesian formulation. Again, we start with an uncertainty set P, and this might be the set of all distributions, and some set of models or a hypothesis space, and we just replace the max from the DRO setting with an expectation and invasion sense, an expectation over a prior that's over the uncertainty set. So we're seeking to minimize the Bayes error in that particular sense. So the way we formulate this in practice, rather than sort of trying to think about a prior over all these distributions, we just impose independent priors over the n0 of x at each value little x. And a simple way to do this is just by reference to the observable function at 1 of x, just say, how far do we think the unobserved regression is from the observed regression at any given point? And again, this could be the same over the whole range of x. It could vary sharply, it could be parametric, it could be whatever your domain expertise consists of. And again, we get sort of very simple and intuitive closed form solutions here, which actually only require us, so these utilize that expansion that I showed earlier, but they only require actually the expectation of the prior over n0 of x at each x. So we don't even actually have to specify a full prior at each value. We just need to suppose that we have some family of priors at each point that has a constant mean. So we just need a value expected by n0 of x. And again, this is easy to estimate from the data. So all we're doing here is we're estimating the missingness propensity, we're estimating this M1 of X, and then we're just sort of smoothing it back towards some prior on the missing portion. Here's just some empirical results. This is semi-synthetic data because, of course, we pose missingness not at random. And briefly, what we find is that, so this is the priors here are very crude. We just suppose the prior is that there's a constant difference across the entire range of X between M0 of X and your estimated M hat 1 of X, whatever your model says when you regress Y on X in the observable data. And what we find, so these models coincide at 0, the baseline predictor, which just uses the observable data, and the sort of base smooth predictor that I showed on the previous slide. At 0, they coincide, and what we find is that if you just get the average sign of this difference right, not even at every point in the range, but just on average, then you can improve over this baseline model. Of course, if you're very wrong on the left-hand side of these, you can do much worse than the baseline model. So, yeah, some intuition here that if you have some kind of domain expertise that's not even necessarily particularly rich, you may benefit from doing this kind of smoothing. Okay, and then our last solution is active learning. This arises again in a business setting because sometimes businesses are able to purchase data from data brokers that fills in some of these initially missing values. And so we frame this as pool-based active learning, which means we partition our initial data set into the labeled data, which is fully observed data, the unlabeled data, which is the data with the outcomes that are missing. And then over some number of rounds, which you might decide dynamically, we score the unlabeled data points with an acquisition function, acquire the top scoring points. By acquire, I mean we somehow pay to get those labels, to have a person label them, and then we update our predictor using that new data somehow. So the primary innovation, I suppose, here is that we keep track of this D. So typically, in active learning, as you acquire the data, you put it into the pool. You don't keep track of whether that data was initially missing or not. There's not necessarily any reason to, except if the data is missing not at random, then the D actually carries residual information about the outcome. So in this second red box here, as we update our model, we're actually training a new model on both X and D. So we're regressing on the features and the missingness indicator, and then we're parceling that out using that initial expansion to come up with our final predictor. And the reason this improves model performance, again, formally, is just that missingness not at random precisely means that D is not independent of Y conditional on X. So there's some residual information there, even once we've accounted for the observed features. So we're basically tracking through the entire process whether the data was initially missing or not, because something about the process that gave rise to that missingness is itself informative about it. And we can formalize this in an information theoretic sense. So if we consider the minimum attainable mean squared error for any predictor that's a mapping from just features X versus any predictor that's a mapping from the features X plus D, we get this ratio of these lower bounds. And that's a function of the conditional mutual information between D and Y given X. And we see here if that conditional mutual information is 0, meaning in fact we're in the missing at random setting, not in the missing not at random setting, then this ratio is 1. So we don't get anything from added D. But as long as there's any amount of information there, this ratio is larger than 1, meaning we can potentially improve performance by introducing D into the predictor. The second aspect we consider is how to modify acquisition functions. And this is a very heuristic insight, but the insight is that when the missingness is large and 0 of X is what contributes the most to M of X. So we just multiply by the observability propensity or the estimated observability propensity. So we take any existing active learning procedure, take that acquisition function, and then just kind of heuristically multiply by this propensity. Here are some results. So the 4 solid lines are what happens when we included the indicator D in our model. The 2 dashed lines are like a traditional approach where we don't, and then we add different acquisition functions on top. And what we see, and this is representative of results across like 35 benchmark data sets from OpenML, is that we improve both in terms of speed of learning and the lower asymptote when we include D. And the pattern is less clear for whether multiplying by this propensity score is beneficial or not. Again, that was a very heuristic thing to do, so we didn't necessarily have an a priori belief about whether that would help. That evidence is a little mixed, but including the missingness indicator D in this setting is definitely beneficial. All right, so just to summarize again, this is what we sought to address, the issue of bias that arises from missingness not at random. We consider these 3 different solutions: distribution or robust optimization, Bayesian regularization, and in the case where we have the option of acquiring additional data, active learning that's precisely targeted to this setting, which is not something that we had seen elsewhere. Thank you very much.
Thanks a lot for the nice presentation. Any questions?
Thanks. Very, very cool approach. I was just wondering so the acquisition function is usually known to be decisive for the performance of active learning. So I was just wondering, do you think it might make sense to first have the algorithm choose new labels to acquire that do not have any missing data, so to give the algorithm a chance to learn the true data generating process better, and then over time allow it also to acquire samples that have missing data? So in the hope that it now can fill the gaps a little better?
Yeah, that's an interesting question. So this would be something outside, I guess, the strict pool-based active learning. Some sort of hybrid of so you're saying you have access to completely unlabeled data set, and then you have access to a data set where just the outcomes are missing, and you might want to sample from this one before. Yeah, that's an interesting idea. We hadn't thought about this. So the answer is no, we haven't thought about that, but yeah, I mean, I think that might make sense depending on the size of your initial data set, because this also hinges on having a good estimate of the missing propensity, which I think is what you're getting at, right? Yeah. So yeah, that's an interesting idea.
Thanks for the nice talk. Now, I'm wondering, now coming from the hierarchical Bayesian modeling community, so what's typically done in practice is this mice approach, so multiple imputation, where you create different replicas of the hierarchical data set, because in hierarchical Bayesian inference, missingness is almost always a problem, and what people, practitioners typically rely on the natural shrinkage property of hierarchical Bayesian models. Do you think your approach may be applicable in these settings to get even better estimates in the case where we have a missing non-attributed process?
Yeah, I can't say I've thought about that specifically. I mean, imputation in general, I guess not specific to the Bayesian setting, but like imputation in general only really works provably, at least in the missing at random setting, right? So I suppose that would depend on whether your priors are meaningful in some sense, right? So yeah, you're saying like somehow render this part hierarchical.
Yes. So the whole regression is now regression with the hyperpriors.
Right. Yeah, I don't know. I mean, I think everything here depends on the quality. I mean, besides the quality of your initial estimates of pi of x and n1 of x, on the quality of your priors here, like it's pretty easy to see here. So I guess I could imagine that either amplifying, if you have a really bad prior, amplifying that effect, or if you have a good prior, I can imagine it amplifying in either direction. Yeah.
It could definitely be an interesting direction, because it could be a huge thing for hierarchical modeling.
Yeah, no, thank you for the suggestion. That's interesting.
Any other questions? So in the chats. Okay, thanks again for the nice talk. Okay. I don't know if the first speaker is here. I'll be the Supreme. If not, then we go.
You got any email from them?
No, I was checking. Then we move to next invited speaker, Yori. I'm going to check it.
Is available, we can start is available, we can start talking.
The thing is not online.
Stop your share.
Okay, then maybe I would use this time to hang the posters and we wait for next speaker to be online.
Yeah, good idea. So authors for the next focus session.
So we just yeah, hang them in the back. And then we come back to help us to talk with your
Yeah. Yes. Okay. I think it's, but yeah, I mean. That's a good point. Yeah. Let's get. Oh, yeah. Yeah. Oh. Yeah, we didn't worry about that again because like worst case, T does not think that's not very good. Yeah. Even if sense. That's good about it. Yeah. Yeah, it's not. It's hard. You're very close to this. Except insofar as we have the smallest.
and then you might be hurting yourself, but I don't know. Empirically, that was something Charlie never wrote. Yes, that's one. So we turn on.
Aaron has showed up.
Yes.
So. It was the other movie we talked about. So.
It's like that, so. Always way. No, true. I could just, I'm the same way.
Yes.
Yeah, somebody first comes these things. I didn't know that's one.
Yes. Just share time. Okay, we have Jörn in the participant. So we should also talk about foundation models that can tell us that they don't know. So Jörn, the floor is yours.
Oh, thank you. Can you hear me okay?
Yes.
Given,
Yes,
let's get the people from this.
Okay, Jörn, just wait a couple of minutes. People are coming.
Yeah, okay. I'll set up the
Cheers.
slides in the meantime.
Okay. Okay, you can start.
Can you see this okay?
Yes, you can.
Yes.
Nice, okay. Yeah, let's wait. Let me know when you want to start.
You can start, please, Jörn.
Yeah, okay. So thank you for the opportunity to give a talk here today. I'm going to talk about foundation models that can tell us when they don't know. This is based on several collaborations with a postdoc of mine, one of the students, and as well as some collaborations with collaborators in astronomy. I'm Jörn Gall, Associate Professor of Machine Learning at the University of Oxford. I'm going to start with how do I get rid of this thing? So this thing is blocking my view. Nice. Okay, I'm going to start with some quick overview just to get everyone basically on the same page in terms of terminology, in terms of notation. Deep learning is built of conceptually very simple models. You give me some data, X and Y, like images and labels, and I define a neural network, basically given some images as W, I'm going to do a fine transformations of W times X, feed it for some linearities, do some more fine transformations. My objective is to find some W's for which the result of this computation, this Y tilde, will be as close as possible to Y for all data points. This like simplicity is quite useful because this allows us to build in a modular way very, very complex models from these simple building blocks. We can build stuff as complex as ChatGPT and using transformer architectures and so on. And the simplicity got huge amount of attention from practitioners and engineers to give us very good software tools that scale well with data and compute and has had really big real-world impact. At the same time, these sort of tools also have a big limitation. They can't really tell us what we know, what we don't know. These sort of tools with deep learning models are often perceived as uninterpretable black boxes, which are easily fooled, causing concerns in AI safety, and crucially rely on big data. Surprising thing is that you can try to tackle all of these problems over here if we have a notion of uncertainty in deep learning. So why should we care about uncertainty? Let's say that this is like the same introduction I gave a talk, so you can like zone out if you want for the next minute or so before we actually get to the interesting stuff. But why should we care about uncertainty? Let's say that you have an idea for a new startup, you want to build a dog breed classifier. Basically, users upload pictures of their dogs, and you can tell them what dog breed that would be. And obviously, you're going to have some user going to go on your website and upload this picture of something that I never saw before. I don't know what this is. I don't know how to classify it. I don't know if I should give you an answer of what dog breed this belongs to. This might sound like a contrived example, but we have the same issues in decision making, in physics, in life sciences, in medical question answering. We need a way for our models to tell us when they don't know and when we shouldn't trust their outputs. Uncertainty also gives us an insight into the black box when it fails. We can, for example, see where should we not trust the prediction. This is actually an example from autonomous driving system, a vision system that is used in one of the earlier components in the autonomous driving pipeline, in a segmentation model that is used to take each pixel and tell us whether it belongs to a pedestrian, to a car, and so on. And this is the resulting uncertainty map that you would get from such a system. Uncertainty can even be used to identify when someone tries to attack us with adversarial examples. And lastly, we need much less data if we label only where the model is uncertain, which allows us to avoid wear and tear in robotics, as well as wasting expert time in medical applications and so on. So we need a way to talk about uncertainty. The language of uncertainty is probability theory. And specifically, I'm going to talk about Bayesian probability theory that has its foundations in the 1750s. When we apply that to information engineering, we get Bayesian modeling, where instead of just trying to find a single function that explains the data, like the red one, for example, or like the single function that maximizes probability for observing the data P of X condition theta, we can try to find a distribution of all possible functions that would be consistent with the data. So over here, it will be the red one, the green one, the blue one. Basically, we try to find the probability of all the thetas conditional on X. Bayesian modeling is built on solid mathematical foundations, traditionally perceived as fairly orthogonal to deep learning. There's been lots and lots of research over the past 5-10 years trying to combine these two together. There's models like approaches like ensembles or doing job at the test time, repeating basically the evaluation 10 times, and then looking at the variance or the entropy, basically the disagreement of the different predictions at a specific test location X star. Basically in code, if you give me the point, you want to evaluate the system at a test point X star equals 3 in this example over here, then you're going to evaluate the model either like free and ensemble models, free ensemble components, or do chop-it like 3 times. Each time you're going to sample a new function. Once you're going to get the orange function, prediction is going to be 0. Another time you're going to get the green function, and prediction is going to be 1. Another time you're going to get the blue function. This is going to be 50-50. And then if you look at the mean, you're going to get prediction 50-50, but the variance will be high, telling you maybe you shouldn't trust the prediction because there's lots of possible explanations of what the data, what the function might be that would be consistent with the data. So, okay, all nice and well. We have some tools for uncertainty estimation. We can use that, for example, we can look at what will be the CO2 concentration in Mauna Loa, Hawaii in 20 years' time, take some neural network, feed it with the data. Normal neural network gives us very confident, incorrect prediction. Bayesian perspective gives us still an incorrect prediction, but at least it tells us, I don't know, we have high uncertainty envelope over here. Now that we can capture uncertainty in deep learning, we can do lots of fun stuff. We can refuse to answer questions when we don't know the answer in a generative question answering system, for example. Or we can detect ambiguous questions and ask for clarifications. Or we can do human in the loop AI. Actually, not so fast. With large language models or foundation models, we can't actually afford to train multiple models for an ensemble. So the stuff that I started from is just taken for granted, but oh, we actually have good tools for uncertainty estimation in deep learning. Just do 10 forward passes with dropout, or just train the ensemble, train 10 replicas of your model. Fine if you want to do that in a vision model. You're not going to do that with a GPT model. You're not going to train 10 replicas of your GPT-4 model when training a single model costs millions of dollars. It's actually not bad. It's not just that. It's not just the issue of evaluating, training the model 10 times. Even if you do train the model 10 times, so let's say you do 10 API calls to your model in order to get 10 utterances generated for a question. Let's say that you ask the question, what is the capital of France? You ask the model 10 times, what is the capital of France? And you're going to get, well, 3 times over here, you're going to get 3 different utterances. The entropy of the multiple utterances in language generation doesn't actually capture what you think it does. So on the left over here, I have model A that I asked the model, what is the capital of France? I asked the same question 3 times, and I got the answer is Paris with probability 0.5. Once I got the answer is Rome, probability 0.4. Once I got the answer is London, probability 0.1. Basically, we're building a histogram of the distribution over the sentences, utterances themselves. On the right-hand side, I have model B over here. I ask the same question, what is the capital of France? Generate multiple answers. I get the answer Paris, probability 0.5. I get the answer, it's Paris, with probability 0.4. I get the answer London, probability 0.1. Which model do you think is more uncertain about its answer? So show of hands, I can only see 2 people in the video, so the 2 people that I can see at least, show of hands. Who thinks that model A? Nice, thank you. Who thinks that model A? Show of hands. Who thinks that model A is more confident in its answer? Who thinks that model B is more confident in its answer? Okay, very good. You're all incorrect. The answer is that both of these models actually have the same entropy. I'm looking at a wall now. Can we look? Actually, can we keep the camera at the audience, actually? Thank you. Both of these models actually have the same entropy. If you evaluate the entropy of this probability vector 0.5, 0.4, 0.1, you're going to get entropy 0.31. If you evaluate the entropy of model B, 0.5, 0.4, 0.1, you're going to get entropy 0.31. So even though the left model has high probability for multiple cities, the right model is very certain the answer should be Paris. Both the models give us the same entropy for the output probability vector. And therefore, if we just threshold entropy to decide whether to trust model answer or not, we're going to fail. I'm actually curious. Can we do audience participation? Can I hear the audience?
Yes, you can.
I think you can. Yeah.
Yes.
Okay, nice. Why do you think that's the case? Why do you think we have this failure over here?
We have microphones in the ceiling. Go ahead, talk freely.
I guess the entropy is just defined over the, it doesn't care what is inside the random variable, it just cares about the probability.
Yeah, exactly. Basically, we define the entropy over the outcome space. And the outcome space over here is not the thing that we want to, the outcome space of utterances generated by the model is not necessarily the thing that we want to look at how dispersed this distribution is. Because we can actually have high syntactic variability, which we don't really care about. So the entropy of output utterances is high when we have high syntactic diversity, whereas what we care about is actually semantic diversity. We care about the fact that these answers are semantically diverse. And we don't care about the fact that these answers from the model B are syntactically diverse. Basically, we need to define an equivalence class we need to define equivalence classes C over the outcome space, the output utterances S, and match together utterances which are semantically equivalent. I don't know, should I go into them? Let's go into the mathematics. We have lots of time. Yeah, we have lots of, and I have half an hour for the talk. We still have 20 minutes. Is that correct?
Yes.
Okay, nice. We have lots of time. So we're going to change our model. So we're going to define a new model, which is going to be a function of the previous model. I'm going to change our model output to be the semantic class C, marginalizing over utterances with the same meaning. So I'm going to define probability of random variable C, taking value some outcome semantic class C, conditional some input question, to be the sum of probabilities of all the output utterances, all the sentences generated as an answer to the question that belong to the same semantic class. And then we're going to look at the entropy of this modified model. We're going to look at the entropy of this P of C condition X, which can be validated as just you plug in the integral of the sum over here into the entropy definition. This sum is actually intractable. There are infinitely many utterances that could have the same semantic meaning. Language is infinitely compositional, and if anyone in the audience has done NLP before, you would know that there's actually evaluating this thing over here is actually very deceiving. We can try to approximate inner integral with Monte Carlo estimation. So P of C conditional on X, which is the sum over utterances, P of S condition X, is just the expectation with respect to the random variable sentence, generated output, condition X, of the indicator variable of probability, indicator variable, does the generated sentence belong to the generated cluster C, or to the equivalence class C. And that just gives us 1 over n, the probability that a generated sentence, like we got from the 10 generations we did before, times the indicator of does that generated sentence actually belong to the semantic class C. So basically what we do is we generate 100 or 10 or whatever, how much budget you have, sentences for the same question that you ask from the model. And then you look at does that generated, how many, like you collect all the sentences belong to equivalence class C, and then you sum the probabilities for those sentences, then you divide by n. You can also approximate the outer sum with Monte Carlo integration. So we have a sum over the equivalence classes. We don't know in advance all the equivalence classes. This is actually very not trivial by itself also, which we can approximate in a slightly ad hoc way by just doing clustering over the actual 100 generated sentences that we generated from the model output, or 40 generated sentences that we generated from the model output. So we do clustering of the semantic equivalence classes. We basically try to do clustering by entailment. So we look at, do I have a slide for that? I don't have a slide for that. I do have a slide summarizing what I just said. No, actually, let's go over this slide. Okay, we did Monte Carlo integration to the outer sum over here with a cluster CI condition generated from the distribution of the clusters condition X. So in practical terms, what we implement is the following algorithm. We generate a set of answers from the model, Sn, and then we cluster them by semantic equivalence class, like something like, what we use, like dBeta, I don't remember. You look at bidirectional entailment, basically. And then you compute the entropy with respect to the equivalence classes CI instead of the sentences themselves. So now model B has lower uncertainty than model A, as we would expect. So model A, we just have 3 clusters, 1 cluster for Paris, 1 cluster for Rome, 1 cluster for London, and therefore the semantic equivalence classes will just be 0.5, 0.4, 0.1. Entropy stays the same. On the other hand, model B clusters together Paris and its Paris because each one entails the other. So we have a single cluster that has cumulative probability 0.9. We have an answer London, which has probability 0.1. And the entropy of this new output space, 0.9, 0.1, is going to be 0.16. So we have much lower entropy, and we can actually say we can trust the output from the model B more than the output that we can trust from model A. With this practical uncertainty at hand, we can now refuse to answer questions when we don't know the answer. And we have some metrics over here of like AURC as a function of model size on COCA and trivia QA. I'm not going to go in detail over this plot, but it works well. I don't care about the details for that. Higher is better. More interesting, let's use this uncertainty to do some fun stuff. So now we have a new tool to detect when the model doesn't know the answer to a question. How can we use such a tool? Let's say that I use a assistant language model, ChatGPT or whatever, and you ask it a question. On what date did you land on the moon? The model is going to give you this answer. He landed on the moon on July 20, 1969. Can anyone see an issue with this? We have missing information over here. There is no way to answer this question as it's currently posed, but this is an ambiguous question, basically. What we would want the model to do is to say, well, what do you mean by he in your question? Then you can clarify, actually, I mean Alan Bean. Alan Bean landed on the moon on November 19, 1969. What we want, imagine that this is like a medical generative question answering system using medical domain. You don't want your system to give an answer when it doesn't know the answer. You would want it to try to collect all the required information or required evidence that it needs in order to give a correct answer than just making some stuff up. So what we can do, for example, is user poses a question. Instead of just directly giving an answer, we're gonna follow this flow chart. We're gonna use some tool for uncertainty estimation to detect whether we can actually answer the question or not. And we're going to define by proxy that if we can't answer this question, then hopefully if we manage to get more information, we might be able to answer the question. So we're going to detect whether based in the uncertainty is low. We're going to say, fine, this is not an ambiguous question. Jump to the end and give an answer. If the uncertainty is high, flag this question as ambiguous, and then try to ask a clarifying question, collect additional information, and then condition on the original question and the additional information, try to give a final answer. And over here, we have a very nice example of what this looks like. So we can generate clarifying questions when we detect a question to be ambiguous. Step one, user asks a question, and the question is classified to be ambiguous. On what date did he land on the moon? This is what the user sees. This is the internal representation that the model has for the world. The internal representation that we use over here is a language-based interface. So a different way of saying like prompt engineering. So we basically represent as the user asked what date did he land on the moon. The bot says, in order to answer this question, like we already decided this is an ambiguous question, we can't answer that. So the bot tries to generate a clarifying question, step two. The bot says, in order to answer this question, I have to ask the following clarifying question. We use some language model to generate an utterance of how do you complete this internal dialogue? Who is he? You serve back to the user, who is he? The user provides clarification, Alan Bean. Internal representation for the bot, user on what date he landed on the moon. Bot, who is he? User Alan Bean. Bot, complete the sentence. The bot generates an answer, November 1969, which is served back to the user. How do we evaluate this? So we can't actually evaluate, we can't generate user responses for each question in our corpus. So a naive way of evaluating such a system, so we come up with some system that allows us to generate clarifying questions, but a naive way of evaluating that is to collect some ambiguous questions, get the bot to, every time you do a small tweak to your system, get the bot to generate a clarifying question, and then get your student to sit down and answer the clarifying question. And then the bot generates a final answer, and then you can look at, is the final answer correct for the ambiguous question that you had. This is a very inefficient way to evaluate things, mostly because the student is not going to sit all day long and answer 500 questions for each trivia QA question every time we do a change to the model. We need to find a better way of evaluating such systems. And we can take some ideas from active learning for that. We can use an oracle that has access to privileged information. Basically, what we're going to do is we're going to do the following. We start from a prompt. This conversation between a user and a question answering. This is a conversation between a user and a question answering bot. Either if the user wants to get an answer to the following question: what date did Alan Bean land to the moon? We plug in the ambiguous question that we had in our corpus. On what date did he land to the moon? We plug in a clarifying question the bot generated. Who is he? Like the bot that we want to evaluate to see whether this clarifying question actually makes sense. Who is he? And then we simulate what the user would say using a language model evaluation system. So this language model has access to privileged information, which is the intent of the user who generated the ambiguous question, in order to say whether the clarifying question actually asks for the correct missing information. Using this Alan Bean answer, we can plug that back into a system and evaluate whether, whether the missing information that was dropped from the original question is correctly retrieved. I hope that made sense. I might have made you more confused. How well does this thing work? We can actually avoid quite well asking for clarifications. We can avoid asking for clarifications with unambiguous questions, and ask and for ambiguous questions, we can ask for clarifications to improve performance. So over here we have a plot. Again, we have AUROC. It's a standard measure for performance for when we have uncertainty for performance for uncertainty estimation. So we have GPT, pointing baseline, CLAM, which is what I just looked at. And we can see that detection of ambiguous questions works very well at 0.9 compared to default GPT. I don't know what we did over here. And when we look at adjusted accuracy, we have performance very high compared to just default GPT giving some answer without actually asking for clarifying information, as you would expect. And compared to always asking for clarification, we basically even outperform every single time asking for clarification, which is the other naive solution over here, which would have very bad AUROC because it doesn't detect when you should ask for clarification. So in summary, this works well. It's 5:02. I don't know if we should finish and take questions or whether I should talk about the other stuff. I have some foundation models in astronomy as well. Do we have questions from the audience, or should I go through the other stuff?
Any questions? Yes, we have.
Okay. Maybe one question is, I guess maybe you do AUROC, so you don't pick a threshold, but how do you threshold like when to, ask for more information or not ask for information? Because like I'm guessing you're thresholding the entropy scores somehow.
Yeah, we are thresholding. That's a good question. I'm not sure how we're thresholding. Usually, to threshold to decide when to ask for, when to refuse to perform prediction, or in this case, when you should ask for clarification, you would. There are different ways of approaching that. For example, you can take your training set of questions that you saw training time and compute the entropy for each one of those questions. These would be questions that you shouldn't ask for clarification because they shouldn't be ambiguous. And then you just take the upper quantile, and then you say anything above that, I'm going to ask for clarification. Another way to do that, if you have access to some test questions that might be asked as test time that will be ambiguous, you can use it to do a histogram for the entropies, for the questions that are confident, for the questions that are ambiguous, and then you can use that to decide on a threshold that will not select too many of the questions that are confident and would not ignore too many of the questions which are ambiguous. I hope that answers the question.
Yeah, thanks.
Yeah. Can you hear me?
Yeah.
Yeah, my question here is, for the large language model, what happens if it does not output the uncertainty? So right now, it looks like you're using the ensemble method, right, to generate the uncertainty.
No, we don't use them. Okay, so what we do here, actually, I can go back to this algorithm. Where's the algorithm? It's fine. I go to this example. We actually use a single model, and we look at the predictive distribution of the single model. So we don't have multiple replicas of the model. We just, all of these experiments actually run using GPT models, using API access, looking at the predictive distribution and evaluating the distribution, evaluating the not the histogram, but evaluating the empirical frequencies of the utterances generated by the from the predictive distribution, which would have high variance for utterances where we have where the model doesn't know the answer.
But this is just a softmax probability, right?
So again,
this is only the softmax probability.
These are the softmax. Yeah, so these are the softmax probabilities.
Yeah, they tend to be overconfident.
So this is interesting. What we found with models like vision model, so this small model, this is actually a very interesting comment because this is very much not obvious. Like you sample a single model, you get the gradient function, and then it might be very overconfident. If you just use the softmax probability for the gradient function at point x equals point x3, you're going to get overconfident prediction, or the answer must be 1, in this case, like the top one. What we found is that with transformer models, the predictive distribution actually is, I don't want to say better calibrated, but people in the community some people in the community would call that better calibrated. What I would say is that when the model doesn't know the answer, it will give you, every time you do, like if you ask multiple answers for the same question, it will give you a very diverse set of answers. So the model actually, there are some papers also that have some claims that large language model-based transformers behave like Bayesian marginalization. That's a bit debatable, but at least empirically we observe that the softmax probability for those models does have the property that we have high diversity, high syntactic, but also high semantic diversity when the model doesn't know the answer. When the model is trained on a question, like is posed with a question that it cannot answer.
Okay, thank you.
Well, thank you for the question. That's a very good question, but is often not asked. People often don't even notice that. Another thing over here, which is interesting, is that you don't necessarily, like I do actually talk about doing multiple utterances for the same model is expensive. You don't even need to do multiple utterances from the same model. You can use the beam search that you do in order to generate multiple utterances without having to do 50 forward passes for your massive transformer model, where doing a single forward pass is going to cost you like a few 20 cents, I don't know. So there are actually ways to make this practical in terms of actually deployment. There are also open research questions of why does model have the property that you just asked about. As I mentioned, there are some papers that claim that. I'm not too convinced about those papers, even though so I'm not too convinced about the theoretical argument in the paper, even though empirically we do observe that property holds. Can we take maybe like one final question? Are there any final questions?
Yes, we have 2 more. Thank you. Just a quick question. If you've read Anthropic's reports from last December, LLMs mostly know what they don't know. They say that the behavior in terms of uncertainty changes like vastly between 1 billion and 54 billion models. I was just wondering if in your experience you have the same.
So can you repeat the question again? So about the
behavior between like very small models like 1 billion and very big models 54 billion.
We observe that as well, yeah. So one quick comment about the Anthropic. There's an Anthropic paper actually had some really interesting stuff in the appendix. I think the paper do large language models know what they don't know. There's some really interesting stuff in the appendix. They propose a couple of methods to try to estimate uncertainty, which are complementary to what we talk about over here. One of them is asking the model very confident about your answer, like what's probability of P true or something like that. And there's another one which is following similar line of thought. So similar ideas of like embedding linear regression. Both of them, interestingly enough, if you look at the appendix results, work very well in distribution, but fail out of distribution, which seems to be complementary to what we observe over here. These things work very well out of distribution. I don't think we actually evaluated that much in distribution. We do observe that with smaller models, we get less variability in the generated answers. So I do agree with that observation that we need larger models in order for the model to be able to generate semantically meaningful, diverse set of answers, but we can actually use to estimate the higher uncertainty.
Hi, I'm wondering about questions that really do have diverse sets of correct answers. So if I ask, for example, how do I build a model to predict Y from X? And one model always tells me train a neural net and another is capable of mentioning many different methods. I might prefer the second one. Does that fall outside this framework, or is there a way to relate that to this?
That's a very good question. So I'll try to rephrase the question. So the language is very multimodal, and there are lots of sentences, lots of questions for which there would be many correct answers. Either because there actually are many correct answers, or because your corpus has lots of diverging opinions about what the answer should be. If you ask a non-RLHF model who won the 2020 election, you would find that there are lots of different people on the internet that think that it wasn't Joe Biden who won the election. And like language models are just a mirror of the corpus that they're trained on. When you have multimodality, you're going to have high semantic diversity as well, and that would also have high uncertainty. That is an example of high rhetoric uncertainty. Basically, what we talked about over here is an example of capturing when the predictive, either epistemic or rhetoric, is high. How do we decouple the two? I think that's still an open question. How do we find when the model has high multimodality, but it's confident, but there are many different ways to get from A to B? Or on the other hand, the model is just hallucinating different answers? I think that's still an interesting question to dig into.
Thank you.
I think we're past the hour, so I'm gonna jump to the last slide and just say thank you. We missed lots of fun. Thank you very much for all the questions, and thank you for the opportunity to give a talk here today.
Thanks, Yarin. Then with that, we go to the next poster session, which will start now until 4 o'clock. So I'm going to share. There is an online pre-recorded poster session. I'm going to the first session, put it in a loop in the Zoom link and broadcast it in the other session.
Hello, my name is Yelizaveta Semenova, and I would like to present this work on solving the problem of shifting administrative boundaries in Kenya to map malaria prevalence using deep learning and MCMC. This is joint work with Swapnil Mishra, Samir Pat, Seth Flaxman, and Julieta Unwin. The problem we're solving is the one of mapping malaria prevalence in Kenya. 1% of the population were still at risk of malaria. It is a challenging task to track the progress of malaria surveillance programs in countries like Kenya because administrative boundaries there changed in 2010 from containing 69 units to containing 47. The map on the left shows old boundaries and the map on the right shows new boundaries. There is a few other challenges associated with spatial modeling of diseases. The first one is that when we work at administrative unit level, the spatial models often rely on adjacency-based structure. This approach completely ignores that processes are continuous in space. The second issue is the one already outlined, that is the change of support problem. And the third issue is that in spatial modeling will rely on Gaussian processes, which represent a computational bottleneck. The contributions of this work are as follows. First of all, we use a recently proposed methodology called PRIA-VAE. It combines deep learning and allows fast and efficient fully Bayesian inference with Markov chain Monte Carlo. We also view spatial processes as continuous and then aggregate them to the district level. We provide a solution to the change of support problem by encoding the aggregated Gaussian process priors with variational autoencoder. This method is faster and more efficient than state-of-the-art Bayesian models estimated with Markov chain Monte Carlo. The rest of the presentation consists out of two parts. In the first part, I will summarize the PRIA-VAE method, and in the second part, I will show how we applied it to the change of support problem. Details of the PRIA-VAE method can be found in the corresponding publication. The PRIA-VAE method tackles the so-called small area estimation problem. That is the problem of spatial modeling with Gaussian processes, and the inference is done using Markov chain Monte Carlo. PRIA-VAE method allows to perform inference faster and more efficiently than the one relying on the Gaussian process prior. It does so by replacing Gaussian process prior draws at inference with the draws obtained from the decoder of a variational autoencoder. The results are that such inference is faster and more efficient.
In addition to that, we're also learning
All the inference that is used both in PRIA-VAE and AG-VAE methods is done using probabilistic programming languages where all user needs to specify priors and likelihood. We assess convergence by looking at the Gell-Mann-Rubin statistics and efficiency by looking both at runtime and effective sample size. The goal of the PRIA-VAE method is to replace the Gaussian process prior with a quantity that behaves better at MCMC inference, and that is the decoder of a variational autoencoder. This variational autoencoder is trained by using data obtained as draws from the Gaussian process prior, which is both unlimited in quantity and is perfect in quality because the draws that we obtain are absolutely noise-free. The PRIA-VAE workflow looks as follows. We start by fixing a spatial structure. Then we draw Gaussian process evaluations over the structure and use these draws as data for the variational autoencoder. The decoder of the variational autoencoder is then used as a drop-in replacement in the Markov chain Monte Carlo scheme for the Gaussian process prior. This method works because we have replaced a highly correlated structure with an uncorrelated one. Back to the change of support problem in Kenya. We start by fixing the spatial grid, which is artificially created and covers the entire domain of interest. We draw Gaussian process priors over this grid and aggregate them to the necessary level, administrative unit level. The aggregation actually represents the integration procedure, so where we start by thinking of process as being continuous, and then we aggregate it to the level of administrative units. we can stack the aggregates corresponding to all boundaries and the new boundaries into one vector and encode them with the variational autoencoded jointly. The AgVE flow is then the prior-VE workflow modified at the steps where we need to perform aggregation. So we start with a fixed spatial structure of areal units, polygons. Then we fix a computational grid covering the entire domain. We draw GP evaluations over this grid. We perform aggregation to the level of administrative units.
To give this global property density has a large effect on the speed of training. Compared to one ensemble. Kind of quite game tasks.
It was one that we're also trying to something very similar.
Yeah. So essentially it was just this.
Oh,
for when you have only one member, then essentially have this, and then with just a few members, you sort of get the global side as well, and that sort of seems to boost.
So every member is essentially different stuff.
Yeah, so it's an episode.
How do you get it?
So essentially, each episode a head is sampled. So these are different heads of the network, right? The members.
So you sample the distribution.
Yeah. No, for each episode, and then you sort of follow that for the whole episode. That's kind of what gives you the tempo.
Are you assuming that you word?
Yes.
It's not a true.
No.
So there's probably doesn't involve.
Well, there's time steps like in the MVP, like each time step here.
Yeah.
But MVP stays constant. So yeah, good question. Experimental. I think there's ways. This is starting to become kind of a thing where adding more and more ingredients one to the other, which is very quite messy, I guess. But there's things that you could do to make the ensembles more diverse. That was like one of the issues, kind of in diversity of the ensemble. You have to be careful about how you train these. So that's one of the things. Then also sort of the way whenever another sort of ingredient here, I guess, is that whenever the data is totally in their heads of policy. So you're not really throwing away information or anything like that. That's good. But sort of, yeah, I guess there's a lot of variations in the ensemble set of the considered.
The words that try to intertwine with the songs.
Yes.
Oh.
Yeah, many.
Right.
Yeah. Peter, oh, I don't think so. Okay, I'm not sure. But I know bagging is like I guess some okay.
Some people are sort of like overthink in terms of
well, that depends on how they're like training. Diversity is definitely an issue. So I think we don't hurt a lot. But they should in theory. I'm not entirely sure like really the experiment what actually happens. That will also depend on kind of what policies they each converge to, I guess.
And you were saying that this is like a sort of like multi-headed policy. Yeah. Why did you do multiple heads instead of just like multiple full models?
Oh, for patient.
Serious of life, but it was interesting. I don't want to. Maybe if you mind.
So many. So student trying to play for having these massive models like ChatGPT, that is very much more because with its popularity, all the content that they are generating is kind of contaminated all over the internet. And these kind of models require a lot of new data, and either version will require even more data. So it's very probable that these new models will be trained on generated data, and we don't really know what is happening. There are kind of papers that this one, sorry, don't worry, with large scale generative models called future data set that they test 12 models trained with generative data, and they see that the performance is worse. So we were very interested in this idea, and we wanted to go one step further and see what would happen in the consecutive version of the models and what would happen. So what we do is kind of, as a first version of the paper, a very simple experiment about training a sequence of models. So training each next generation of the model with the data generated by the previous one. And as you can see, what is expected behavior that kind of expected that the
Sorry to interrupt. So this isn't a mix of new and old data basically, or do they really only get to train on the data generated in this generation?
Case, only the genetic data. But with a previous version, we do like this mix between generated and new data. And the only behavior that is a little bit slower. Recently, there was another paper about this idea. That's this one, self-consuming genetic models. And they also try it with fresh new data in each generation. And the performance is kind of the same. It's not necessary to see our metrics, but you can see the performance is worse in friend setting certain distance and vertical coverage. And we also tried it in a more simple model with MNES, and we measure it with a classifier to see if the latest data generated version were useful. It's kind of a very stupid and simple experiment, a toy experiment, but it's kind of the first version to try to understand what will happen in the future. What I'm working right now is to kind of simulate this internet behavior. Not kind of how we scale data and how the data is contained in the internet and these kind of things. And also there is a problem in this kind of experiment that we have done is that only participates one model, when in reality there are different models, also a lot of open source models. And also there is a recent paper that says that if you want to publish good synthetic data, you should generate it in an ensemble of generated data sets. So it seems like a promising way to see a more realistic experiments. And in order to prevent this behavior or this possibility or other possible bias, I think that we should start thinking about watermarking the models. Because, for example, Lion dataset, that is a very famous dataset, already is contaminated. So unless we don't put some watermarks on some method to detect generated data, there will be a problem in the future that we don't know. Maybe not this one, that is a little bit the worst case scenario, but in the way of bias or kind of other fairness issues and these kind of things.
Did you study the distributions of the data across the generations? So like, what is the difference between?
We don't, but there are other papers also who do that. And seems like because we are approximating a distribution over time, at the end is very different from the original. So there is like a, but we didn't want to go any further in this toy experiment because it was a little bit simple.
Objective, like bigger models deteriorate slower.
It's kind of the reason of this experiment trying a simple data set. So I think that if the model is very good, able to generate very good quality of data, the performance will be lower. Sorry, the degradation will be lower. So it seems like this is the case. So this is like the worst case scenario, but it's like a start to try to think about the future problems that we will face.
Yeah, I think that was good.
A single track poster session.
Yeah. Private courses. Really been in order. Sorry? Oh, maybe 19 order ready for public. I was saying this. I think it's the year.
I wonder if we can just hold back a little bit.
We have some one word.
So that we can have to break that.
Yes.
I didn't anticipate.
Can we set the schedule?
We are really soon. To have more data with us in the internet.
The cost of generating certainly lower than having.
Schedule. We have which one have been closed there. So then.
Really something just one.
Which one is here?
Yes.
We can do
It's like 1/n. Oh, that's because this is for the zones for you only have counts. There are methods that are use the pseudo counts for continuous space. I guess here the distribution picks up the ensemble heads, but that's not like so useful for you want to do. He also has a chapter like you have, for example, instead of like pseudo counts essentially.
So we can have the breaking 10 minutes. So is that way the last remaining poster? Then we move, I think, back by 30 minutes.
Yeah, there's
Good evening, everybody. I am Raza Imam, along with Mohammad Tala Alam, Mohammad bin Zayed University of Artificial Intelligence. We are here to present our paper optimizing brain tumor classification, which is a comprehensive study on transfer learning and imbalance problems in deep learning models. So, as we know that deep learning and transfer learning models have been proposed in the literature with very higher classification in resolving brain tumor MRI problems. However, most of those scenarios have been focusing on balanced data sets. But when we look on the real world scenarios, most of the data sets are found to be imbalanced. And therefore, we try to focus more on precise classification of imbalanced brain tumor data sets. And in terms of contribution, we try to introduce transfer learning plus a CN model. Most of the current literatures in brain tumor classification deal with just transfer learning with fine tuning. And whereas we are trying to propose a transfer learning plus CN model. And we try to compare 8 of those transfer learning models using various approaches to resolve imbalanced MRI images, classification problem basically. In terms of research objectives, we try to incorporate 8 transfer learning models, which are integrated with our 8 layered CNNs in order to increase the classification accuracy of different 4 classes of brain tumor. The 4 classes that we used is like, first, of course, the no tumor, then the other ones are the glioma, meningioma, and pituitary cancer. And how are we resolving this imbalance problem, by the way? So for this, we have experimented with 5 different approaches. 5 are basically a subset of 2. First is a loss function that we experimented with changing loss functions, and other is like we experimented with changing oversampling methods. The loss function that we use are like the focal loss and the cross entropy, whereas for oversamplings, we use the data augmentation, the standard data augmentation, and the smooth and add-asset method. And we evaluated our models on in different metrics like accuracy, precision, recall, and F1 score. Talking about the data set, so since there is not a particular imbalanced brain MRI data sets in the present literature, therefore we try to make a custom-made data set. We incorporated our own custom data set using several existing Kaggle brain MRI data sets, and we combined them to make a custom imbalanced data sets of aggregated 4,200 MRI images with 4 classes. The first class is no tumor with 1760, and other classes with 858, 1265, and 341 images in those classes. And the validation we use for validation and training, we split our data set into 90:10 ratio, and we then evaluated the model. Moving towards the method section,